Hello and good morning, everyone. I'm Tushar Athavale, research scientist at the Oak Ridge National Laboratory, and it is my great pleasure to welcome you all along with our co-chairs, Chris Johnson from University of Utah, and also Paul Rosen from University of Utah, Christy Potter from National Renewable Energy Lab, and Dave Pagmar at Oak Ridge National Lab. So before we start, I just want to give a little bit of background and information about the workshop. So we previously held three workshops. One that started by Chris Johnson in 2011 at IEEE Viz, and then we had one at IEEE Viz 15 led by Christy Potter. And recently we had this dark stool workshop, which got really good response on uncertainty visualization. So we thought we should be doing these more to address some of the tough challenges in uncertainty viz. Now, about submissions and review process, yeah, we were really excited to see so many good submissions touching on different areas, of uncertainty, right from AI models and different types of data and ways to communicate uncertainty, software and decision making. They touched all different topics. So I'm really looking forward to all exciting talks. We total received 12 submissions and 6 long papers, 5 short, and 1 posters, all great quality. So what we did is we selected 1 best long paper, 1 best short paper, and 2 honorable mention for long and short paper. Now, this was based on overall review scores, overall novelty of the contribution, potential impact actually for the future, and then discussion among chairs. So congratulations to all, first of all, for to who won the best paper awards. First one is about tensor field uncertainty visualization by Tadia Smits and Tim Jerritz. And second one is uncertainty related to ensemble and surrogate models. So we thought these are really exciting topics. Very few work is done in these areas. So congratulations. And then we selected 4 honorable mention, which also touch diverse areas, and we really thought these were good papers. And remaining 6 papers, we have lightning talks. Um, Also, we would like to thank the program committee for agreeing to review these papers on short notice, and they did really great job and give some really good feedback on these papers. Uh, Finally, the invited speakers, we are really pleased to have the international leaders in visualizations who will visualization field who will share their perspective on importance and challenges in uncertainty. So really looking forward to all these discussions. Now, before further ado, let's start. But before we begin, there are only 3 points I want to mention. Please make sure you have given video consent before you speak in this meeting. Then there is make sure your camera is off and you're muted throughout. And then whenever you're not presenting, and then we have a hard cutoff time. So 5 minutes after the session, which is 11:35, there will be a hard cutoff. So we want to make sure we stick with timeline. Uh, so it's my pleasure to introduce today a keynote speaker, Dr. Daniel Weisskopf. He's a professor and director of Visualization Research Center, VISUS, at the University of Stuttgart, Germany. And he received his PhD degree in physics from University of Tübingen. I am apologize for the pronunciation, Germany, and habilitation degree in computer science at the University of Stuttgart. His research interests include visualization, visual analytics, eye tracking, human-computer interaction, graphics, augmented virtual reality, and basically all different areas in Viz. And he is a spokesperson at the DFG-funded Collaborative Research Center on quantitative methods for visual computing, which covers basic visualization research, including uncertainty. So welcome. Unfortunately, he has some voice troubles today. So he sent me a pre-recorded talk, which I will play with you guys. Play, and he should be around to answer Q&As at the ends. So let me share the video and start the keynote talk.
Hello and welcome to my talk on uncertainty visualization, the importance of quantification. We've seen a lot of progress in visualizing uncertainty over the years, with many different contributions from the community. For example, we now have a large variety of visual mappings. The uncertainty bubble map here on the right is just one example. And there's a lot of empirical work to address the hot problem of evaluating uncertainty viz. And there's also much input from the psychological perspective there. Finally, the community has explored many different applications, showcasing the importance of uncertainty viz. However, uncertainty viz is super challenging, and therefore there's still a lot to do in the field. It's great to have the uncertainty workshop this year at Viz. I'm very much looking forward to today's workshop to learn more about the most recent results. And I don't want to cover the whole breadth of uncertainty viz in my talk. Instead, I want to focus on one specific aspect, that is quantification. Quantification is especially important in the context of uncertainty because we are easily fooled. We often lack good intuition of the impact of uncertainty. Therefore, grounding in reliable computational models is critical. I'd like to look into the following aspects of quantification in more depth. First, how can we quantify uncertainty of the input data? Well, how can we model that uncertainty? Second, how is uncertainty then propagated through the entire Viz process? Here, we need methods for transforming the uncertainties. Finally, I'd like to visualize the quantitative nature of uncertainty representations. Let's have a look at the visualization process involved. I'm choosing a quite simplistic version of the visualization pipeline here. At the start, we have some source of data, for example, from measurements or simulation. Then, we collect this data as sources for visualization. After that, we can apply all kinds of transformations to the data, also some machine-based analysis, such as statistical computations or ML. The goal is to arrive at a data representation that can then be mapped to visual primitives and finally rendered. Now, uncertainty should be considered in all of these steps. First, we have uncertainty in the input data and therefore in the data acquisition. And this carries through the filtering and transformation steps. So we need to know how uncertainty is propagated here and how the transformation might introduce additional uncertainty. And finally, we do the actual visualization. This might also add uncertainty. So far, we've only looked at the technical parts of the visualization. However, the goal is to produce images for human consumption. Therefore, we have to consider the user in the overall process, including perceptual and cognitive aspects. But the user might not just be passive. In fact, with interactive visualization, we can potentially change all stages of the Viz pipeline. And of course, we should consider the effects of uncertainty here as well. I will mostly focus on the earlier and technical stages of the process. Alright, here's a brief overview of the rest of the talk. I will start with modeling uncertainty in the input data. Then I will spend quite some time on discussing several examples of uncertainty propagation. Finally, I will show some examples that visualize the quantitative aspects of uncertainty. As a disclaimer, I will use examples from my own previous work, but this does not mean that there isn't much other related work out there. Also, comprehensiveness is not a goal of my talk. Alright, let's get started by looking into modeling uncertainty of input data. The problem is that we are sometimes not sure about the uncertainty in the input data. We are often missing quantitative models of uncertainty. Well, the situation is mostly fine when we are working with ensemble data as input, or when we have generative models of the data, because then we can do statistical aggregation or modeling ourselves. In other words, the modeling part is under our control. To a lesser degree, we know about uncertainty for simulations. Ideally, we have access to the mathematical simulation model and the implementation to extract the uncertainties. However, that's sometimes not possible or just very time-consuming. Overall, with more and more open science, I think that the situation will further improve in the future. The biggest issue comes with many of the off-the-shelf datasets. We might have access to the data, but it might only contain mean values. Even though there might be some qualitative understanding that uncertainties should be involved. However, it might be hard or even impossible to quantify that uncertainty. Well, I think that the lack of such important data is an especially big problem for uncertainty viz. On the next slides, I will discuss some examples how we obtained measures of uncertainty. I'd like to start with an example from bioinformatics. Here it's about uncertainty in secondary structure assignment for proteins. The problem is that there is no ground truth. In fact, there are several computational methods to compute the secondary structure. But these techniques might come with intrinsic uncertainties. And even more importantly, there are discrepancies between the techniques. Our uncertainty model combines both aspects. The image on the right illustrates the discrepancy and agreement between 4 of the techniques. It took quite some effort to access the internal uncertainty measures in some of the algorithms. We did not only have to look into the internal mechanics, but we even had to do some data fitting for quantitative uncertainty in some cases. This shows that data acquisition can become quite involved for uncertainty viz. We can complement the sequence view with a 3D visualization, here with an uncertainty ribbon diagram. The highlighted part belongs to the part shown in the sequence view. The wiggles or fluctuations imposed on top of the secondary structures in 3D indicate the uncertainty in the assignment. For comparison, here's the ribbon diagram without uncertainty. The differences become more apparent when I'm toggling between the two visualizations. Here's another example of a quantitative model. This example shows that fitting a distribution to sampled input data might come with its own challenges. Here the input is a collection of ratings on a categorical scale, more specifically with 5 levels. Just think of ratings between 1 and 5 stars that users might give. Our datasets contained such ratings of subjective image and video quality. Now, the goal is to fit probability distributions to the input data. We are looking for continuous models with 2 parameters, for mean and variance. The empirical evaluation showed that different distribution models have different quality in terms of fitting to the data and in terms of predicting new unseen data. We were involved in a project driven by our collaborators who are experts in image and video quality assessment and statistics. The message is that good models might need quite some expertise from outside of the visualization research community. Despite the usefulness of specific models, just like before, a large chunk of work relies on univariate or multivariate Gaussian distributions or Gaussian processes. Many datasets can be approximated by these distributions, and they have a lot of benefits when it comes to subsequent computations, as we'll see in a minute. It's even quite common to assume independency for the different dimensions of the data, often just because we don't have sufficient access to their relationships. However, this can lead to very wrong results if there is intrinsic correlation. Therefore, including covariance is the first and often most important step to improving the uncertainty model. And such Gaussian modeling has its prominent place. Even if it's not a completely accurate description of the data, it can still be useful as a surrogate model. I'd like to do a short summary of this part of my talk. One big issue is that uncertainty information is not always accessible or even known. Often, we have to do our own reconstruction and modeling of the uncertainty. But this might need substantial domain knowledge and can be hard. We've also seen the high relevance of normal distributions, and covariance is super important to capture dependencies. What would be great for the future? Can we come up with rather generic approaches to do the uncertainty modeling? For example, by solutions for some kind of classes of problems. and another approach could rely on human expertise to fill in the missing pieces. The image on the right illustrates a simple user-controlled specification of that information. Finally, ML and AI models might help do better estimates for missing uncertainty information. All right, let's now look into uncertainty propagation. There are general uncertainty propagation strategies, and they depend on the type of transformation. I will go through the following strategies. First, we might have a fully linear transformation. The second one is for the nonlinear case, but then using linearization. And third, there is sampling with Monte Carlo or similar techniques. When we have a linear transformation, then the means can be transformed the same way. But even for the covariances, we have a closed-form computation. By multiplying the covariance matrix with the linear transformation and its transpose from the left and the right side. And for the case of linearization, we just need to compute the Jacobian and use this for the transformation. Now, let's see these transformations in action. My first example is principal component analysis. PCA is often used for multivariate data visualization, and it's linear. It's based on one global linear map. Therefore, uncertainty propagation is as simple as from the previous slide. The key point that makes uncertainty-aware PCA more challenging is the following. The PCA transformation itself is affected by uncertainty. In other words, it can't be computed just from the means of the data points. The image at the bottom shows a very simple example with just 4 data points and 2 data dimensions. Without uncertainty, on the very left, we have 2 principal components. By increasing uncertainty, we get wider and wider blobs instead of just some data points. Here as normal distributions in 2D. With increasing uncertainty, we also get different PCA axes. You can see the rotation with higher and higher levels of uncertainty. We provide an implementation of uncertainty-aware PCA within a larger toolbox. If you're interested, please check out the poster presentation by Patrick Petzold later in this workshop. And here's another example of a linear transformation. Now it's about time series visualization by STL. The uncertainty model is that of a Gaussian process. Now, the key point is that we could compactly formulate STL as a big matrix A hat. And this matrix works in a large space. This space not only contains the original time series, but it also holds the various STL components. Therefore, the original data is first embedded in this larger space. And then we can do the STL transformation. By a single matrix operation, we can propagate the covariance information to the different components. For example, the seasonal component is highlighted here, with a spaghetti plot of the time series on the left and the covariances on the right. More details will be provided by Tim Krake in his presentation later this week. My next example is uncertainty-aware MDS, again for multidimensional visualization. The non-uncertainty version can be formulated by stress majorization. The stress term compares the original distances in high-dimensional space with the target distances in low-dimensional space. But how can this be extended to capture uncertainty? First, we need to do integrations over the pairwise probability densities. The kernel for the integration looks similar to the stress from before. The key element is how we can represent the distances in target space. Here we introduce a local projection or MDS operator phi that's just around each data point. At this point, phi is a placeholder and not yet known. To compute the phis, we need additional assumptions for simplification. One, and not surprising, we use independent Gaussian distributions. And second, we assume that phi is a linear operator around its corresponding data point. The later assumption directly leads to a piecewise linearization of the nonlinear MDS mapping. The actual computation is still quite involved. We needed quite extensive mathematical transformations to arrive at the final results. Once again, we also have an implementation available in our toolkit. My final example is probabilistic graph visualization. In this example, uncertainty affects the edge weights in the graph. I'd like to use node link diagrams for the visual representation. And I'm adopting the approach of overlaying samples from the distribution of graphs. This means that one sample is now a full graph, as drawn from the distribution of graphs. And we need to overlay the edges and nodes from the node link diagrams for the different graph samples. Therefore, this is an example of Monte Carlo sampling for uncertainty propagation. You can see an example here on the right. The nodes are shown by color-coded regions, and the spread of the regions indicates the uncertainty of the node location, and the edges are shown as gray links. With this zoom-in, we can better see the distribution of nodes and edges. This zoom-in shows region representations of the node distributions along with surrounding boundary curves. The actual sampling of the nodes is illustrated on the right. The different node samples are rendered as little splats. And the final visualization combines both. That is, the splat rendering and the region rendering. Here are the steps that are needed for the probabilistic graph visualization. We first take the graph data as input, along with a model of the uncertainty for edge weights. Then, we generate many graph samples from the distribution. This is the key element of Monte Carlo sampling. In the next step, we compute force-directed layouts for each of the graph samples. Now, the biggest problem is we can't just overlay them, because the different layouts are not aligned in any way. Therefore, we align them by tying them to a reference. Once we have this, we can do the final actual rendering by blending the different node link diagrams. Here's the mini summary of this part. We've seen the different propagation strategies in action. PCA and STL are based on linear mappings. MDS uses a linearization of the MDS operator around the data points. And for a general case of highly nonlinear mapping, we use Monte Carlo sampling for the graph layout. All my examples had Gaussian models for the input data. In many cases, this is important to make the computations tractable. In general, we usually have to think of the uncertainty model and the propagation in concert. They are linked to each other. I haven't covered them in my talk, but perception, cognition, and user interaction are critical for the full process. Therefore, propagation has to be considered there as well. But this can become super hard because models for these parts are extremely difficult to obtain. I see the following research challenges. How can we deal with nonlinear mappings, except for using Monte Carlo computation? Likewise, how can we include non-normal distributions in the propagation process? One promising direction could be ML surrogate models. In any case, when we're using surrogate models or approximations for propagation, how can we check their validity? These checks should consider the nonlinear nature of the full process. Finally, it would be great to have a collection of generalizable techniques. All right, let's now look into visualizations that consider the quantification aspects of uncertainty. Here's one way to organize the large variety of visual mappings of uncertainty. Much work of the community has focused on understanding and improving the approaches on the top of the figure. Different from that, I'd like to pick the approaches from the bottom. Now, we can consider uncertainty information as data of its own right, not to modify the other data visualization parts. Therefore, such multidimensional extensions are typically not even considered uncertainty visualization techniques in our community. However, I think that they are super helpful, especially for expert users. Let's have another look at the STL example from before. The heat map on the right shows the covariance matrix. Therefore, this is a typical example of a VIS technique that directly represents statistical measures. Let's zoom into this visualization. This block shows the covariance within the trend component. We can see that there is just gray at the top and bottom parts of the diagonal. That means there is no uncertainty there. And in the center part, we have a large blob of positive values. In other words, there's a wide range of correlation there. Switching to the seasonal component, we can see a periodic structure around the center, just as it makes sense for an oscillating component of the time series. Unfortunately, the entries in the covariance matrix may become rather small. Therefore, I can also switch to the correlation matrix, which shows very similar information, as can be seen here on the right for a different data set. This figure also illustrates that we can derive other relevant quantities from the matrix, for example, an indicator for correlation length. And this is computed by going from the diagonal toward the left and right in the matrix, or by picking local correlation values, in other words, taking a vertical slice from the matrix. Such derived quantities can be super helpful when designed for the task. Here's one more example, now going back to uncertainty-aware PCA. The factor traces provide a concise representation of the effect of varying levels of uncertainty. They show the trace of the unit vectors of the original data, but now after projection by PCA. Therefore, they indicate the sensitivity of the PCA projection under uncertainty. My final example shows uncertainty quantification in the context of visual analytics and AI. Uncertainty visualization is included, for example, by showing distributions in the flower glyphs on the left and in the heat maps in the center of the image. The goal is to show the reliability of computer vision results and to allow users to fix problems. In this example, we aim to speed up gaze labeling from eye tracking studies by combining computer vision with human intervention. This system uses a combination of views, and several of them directly indicate quantified uncertainties. The overall system lives from the integration of views with user interaction. More details will be provided in the respective talk by Maurice Koch later this week. Let me briefly summarize this part of the talk. I advocate that we should also think of uncertainty information as separate data of its own right. The respective visualizations tend to target expert users, but can provide perspectives that are very different from the more traditional uncertainty visualizations. In this context, derived data can be super helpful, often designed for a specific task. And we can also integrate such visualizations in more complex VA systems. As one research challenge, I see the need for aligning the visualization with the task. Also, it would be great to have a collection of rather general techniques. And finally, the systems typically address expert users. How can they be modified for non-expert use? All right, let me now conclude my talk. With a number of examples, I discussed the importance of proper uncertainty modeling and quantification. Here, it's important to consider the whole visualization process. I've especially looked into modeling uncertainty in the input data and how uncertainty is propagated through the stages of filtering and visual mapping. Human perception, cognition, and interaction are equally important, but I've touched them only very briefly. In short, uncertainty viz research needs expertise from many areas, including mathematics, technical areas, and psychological expertise. I've also discussed that many solutions are quite specific to an application area. Usually, we would prefer more generic solutions for broader impact. One challenge is to find ways to come up with more generalizable methods, for example, by using appropriate surrogates. Here, advances in AI and ML provide great opportunities, for example, to arrive at better uncertainty models for input data, or as surrogates for uncertainty propagation. Likewise, many AI models have intrinsic uncertainty. Here, uncertainty viz could provide new ways for improving AI, especially by supporting explainable AI. Therefore, these are great times to work on uncertainty visualization. I see uncertainty viz as a magnifying glass for viz research in general. After all, many of the general viz problems are even more pronounced when you include uncertainty. For full reference, here are the image credits for this talk. And I'd like to thank all my collaborators. This work was done within SFB TRR 161. This long-term and large-scale collaborative research center addresses quantification in the various facets of visual computing. And one of them is uncertainty visualization. I'd like to thank you for your attention.
I'm uh, I'm not able to start my video. Can says the host has stopped it. Anyway, thanks Daniel for this. All right, thanks Daniel for this great, very insightful talk. I really loved it. I mean, yeah. So I could start asking questions, but we already have a question on Slido. So let me begin with that first. What are the examples of uncertain graphs in real world? I mean, why there is so that's one of the questions.
Yeah, sure. So, of course, the example in the talk was very brief, and there was no application. So one application area we looked into, first of all, I should say that the graph model was that the uncertainty is on the edge weights. So the topology was kind of fixed, unless you say, well, with the edge weights, you kind of change the topology along the edges. But the model is we have kind of a set of vertices, and then there is some distribution model on the edge weights. And one example area we looked into was bioinformatics, for example, protein-protein interaction networks. So there is connections between entities. And why are they uncertain? Well, there's different evidence, for example, literature and simulation and so on. And we also had to do a little bit of tweaking of the uncertainty model because you don't readily get it from the literature. But it was essentially based on the evidence there. Other examples is whenever you do aggregation in the sense that you use aggregation of statistical kind of measures, for example, of time-dependent data. So a simple example would be that you just have traffic connections between cities, varying travel times during night, during day, and you have a number of fixed cities. You have the different travel times. We also use that as an example from the aggregation over time. And again,
Right.
it would be something that's working on the edges.
Yeah, those were really nice examples. One of the questions I had was about machine learning, right, and AI for uncertainty visualization. You mentioned that in both data model side and propagation. I was like wondering, like the training, right? Training the models is always a problem. We don't have enough data. Uh, have you thought, like, do you have some insight on like how this training data could be gathered? One of the things I have thought about is Monte Carlo sampling, like just do Monte Carlo sampling or do ensemble data sets. But if you have any general comments on that.
I think I only briefly indicated, I think that's what I meant by looking into classes of problems. So a little bit, the hope would be that you find not maybe a general, I think that's not feasible, a general one, but that we push maybe in collaboration with the experts in the respective fields, that we gather enough data for certain types of data sets or classes of data. Just one example that we do in Stuttgart, we have a larger research project on simulation technology and simulation science. And it was traditionally very much rooted in traditional PDE solvers and so on. But of course, there's not now much more data integration going on ML. And they came up with, for example, simulation codes that produced specific training data to be learned then with machine learning techniques. Not for uncertainty so far. It was more for learning physics-based ML techniques. But I think then it's only a short kind of step to using at least for these types of data sets. But for other types of data sets, of course, like always, the ML problem is very much connected to augmentation, finding the right data sets.
Right.
And also kind of characterizing what is the right style of data sets.
Right. Okay. Yeah, that was good. There's one more question. We have time for one more quick question, really. What is the consequence of making independence assumption on dependent variables when modeling uncertainty? This is question from Kane Moreland. Yeah.
it can be very wrong. It can be arbitrarily wrong, especially if you do a nonlinear mapping, because then you don't know what you end up with. And I think that's what the community did in the beginning very often, ourselves as well. You just didn't have enough data. You didn't have enough information. And then you just, for example, in FlowVis, we assume that at each location, you have essentially a new particle trace starting somewhere, ignoring that you came from somewhere or that the data set has to observe certain physical characteristics like being a solution to Navier-Stokes. So it can be arbitrarily wrong if you do that.
Right.
If you just look at the scatter plot, it means instead of axis aligned ones, you can have rotated ones if you have covariance. And then, of course, you can do all kinds of shapes there that you could not capture otherwise.
All right.
So covariance is important, but hard to model.
Agreed. Yeah, thanks. In the interest of time, we have to move on, and let's thank speaker again, Daniel, and we can take questions offline later. So
thank you. Thank you for having me.
Yep, thanks. Next presenter is Teddy Schmitz from University of Cologne, Germany. Actually, Tim is presenting, right? So yeah, and it's a best long paper awarded. Looking forward to this talk. Go ahead.
All right. Let me quickly share the screen. I hope you can see everything. It looks all right to me.
Yeah, looks good.
All right. Yeah, thanks a lot for the kind introduction, and I'm very happy to share the work that I've been doing together with Tadia Schmitz. Unfortunately, she cannot present today. But we had been looking into symmetric second-order tensor fields. So that's the kind of tensor that you can find in describing diffusion processes in the human brain or stresses within materials. And especially finding and showing topological features has gained a lot of attention in the last decades. Maybe to quickly recap, tensors are often described in terms of their eigenvalues and eigenvectors, and tensor topology focuses on locations where the eigenvalues have a special relation to one another. So, for example, degenerate tensor locations are those where at least two eigenvalues are repeated, which then typically form lines known as degenerate tensor lines, and you can see them here on the left in the presentation. However, this all applies to only single certain fields, and many of our collaborators do not work with single fields, but they create multiple such fields, forming tensor field ensembles, which resemble uncertainty in their simulations. So in our work, we wanted to look into the uncertainty visualization of degenerate tensor locations in ensembles. And we started by looking into what is known as the mode function of a tensor, which is typically used to extract topological features. It's a scalar function in the range of negative to positive 1, and it can be quickly computed for a single field. And finding degenerate tensor locations is simply done by extracting the 1 and -1 level sets in this function. So our reasoning was actually quite simple. If we can use the mode function of a single tensor field to extract degenerate tensor locations for this single field, we might be able to use the mode function of a tensor field ensemble to do the same thing, well, for the whole ensemble. But we needed to define what the mode function of an ensemble is, and we came up with two options. Option one is the mode function of an ensemble is the mode function of the mean tensor field. So it basically means we take the original tensors of all the members that we have, and we calculate the mean tensor at every location, and then we can take the mode function of this new tensor field. Quite straightforward. And our second option was the mode function of an ensemble is constructed from the combination of mode functions of all ensemble members. So that means we can calculate the mode functions for each and every member, which is quite fast. And we then use mean and standard deviation of this mode value to represent the distribution of mode values at every location in the ensemble. So doing this, we had two new descriptions of mode functions for an ensemble, and using both, we now wanted to design new features that would allow us to effectively summarize the behavior of degenerate tensor locations while also providing an encoding of uncertainty. And we came up with three such features. The first one is what we call the ensemble mean line. And well, using this new mean tensor field that we came up with, it basically allows us to treat the ensemble as a single certain field and apply standard extraction methods to it. So we can basically extract the degenerate tensor line in this mean field, and that's what we call the ensemble mean line. But now we can further enhance this feature with additional information to include uncertainty, such as mapping standard deviation of the mode function to color and radius of the mean line, thus indicating how certain or uncertain this feature is. Our second feature is the ensemble mode tube. We can analyze the distribution of mean mode values surrounding this extracted mean line that we got. And we can use this information to change the shape of a tube surrounding the mean line. Thus, we can indicate areas of higher mean mode values and provide a spatial understanding of the mode distributions, right? Because this tube is shaped towards higher mode values. And our last feature is what we call the ensemble probability band. Because if you remember, we can use mean and standard deviation. We essentially have a distribution of mode values for each location in our ensemble. And we are interested in locations where the probability of mode values being close to 1 is high, because 1 means we do have a degenerate feature there. And we can describe this by a scalar function and can extract isosurfaces within this field. And this is what we call the probability band. So for example, here you can see this isosurface encompasses areas in which the likelihood of mode values being 0.95 or higher is more than 50%. So that's what the probability band is telling us. All right, those are our 3 features that we came up with. So let's quickly look into some results. First, we created a synthetic data set with a large number of members made from adding noise to a single tensor field. And on the left side, you can see the extracted degenerate tensor lines from only 10 of those 1,000 members and displayed in a spaghetti plot, which took quite some time to do. And as you can see, it doesn't really provide you with a good representative of the uncertainty in this field. And in the center, you can see the enhanced mean line visualization as a representative of the whole ensemble. And it's also very close to the original degenerate line. And surrounding it is the probability band, indicating a 33% likelihood of finding mode values higher than 0.95. And you can see both together can do a decent job of summarizing the locations and uncertainty of degenerate features. We then also applied our approach to a simulated stress tensor ensemble, where stresses are simulated in an O-ring. And in this case, for example, we only use 2 members, which have each have a degenerate tensor line, and both are quite close to each other. You can see that on the left side here. And the mean line can summarize this behavior quite well. And it also indicates locations where these degenerate lines are getting further apart. You can see this by color and shape. And the probability band points us towards new locations in the fields that were likely to encompass degenerate tensors as well, which we might not have been able to see before. Similarly, we did the same thing to a set of 8 different simulation results and extracted the degenerate tensor lines. You can see them again here on the left in green. And these lines essentially form 2 bundles, one where lines are very close to each other, and one where they spread further apart. And the mean line can effectively convey the first bundle, also showing their behavior and where they start to spread, but it fails to catch the second one. But the second bundle is caught by the probability band. And so the combination of both the band and the mean line can convey the overall behavior and uncertainty of the degenerate tensor locations. And on the right side, on the top, you can also see that the mode tube can capture this spatial distribution of the lines. All right, so to summarize, in this work, we presented 3 new, if not the first features to analyze degenerate tensor locations in symmetric second-order tensor field ensembles. These are based on 2 different descriptions of the mode function of an ensemble, and they allow us to describe local and global uncertainty of degenerate features. And as a bonus, this is all quite computationally cheap and fast, in contrast to extracting degenerate lines from all the members. But of course, there are limitations. For now, we only deal with symmetric second-order tensors, and we assume that our data is normally distributed. We also made some simplifying assumptions. For example, we ignore triple degeneracies, and because they're structurally unstable, and we do not include notable surfaces, which are other features that we might want to look into. And finally, we would also like to do a user study with experts to see if they can actually analyze their fields better with our tool. We got initial feedback, which was quite promising, but it should be done more rigorously. And with that, I'd like to thank you for your attention, and I'm open to any questions.
Right. Thanks, Tim. That was really nice talk. Very new field, tensor field uncertainty visualization. In the interest of time, we have to move on, but I have one quick question. So I don't see anything on Slido, but I don't think you consider correlation between neighbors, right, for your work. Correlation between neighboring tensors. Is that right?
No,
You're assuming independence. So I think
yes,
based on Daniel's talk, maybe it will be interesting to see how correlation changes this
yes.
visualization.
Yes, so
Yeah,
the
but
only thing that includes a sort of neighborhood is this mode tube, which compares surrounding mode values with the center value. So
right,
this is the only neighborhood information that gets into the thing. Yeah,
got it. Cool. All right, thanks very much.
sure.
So,
Thank you.
yeah. So next we have Sam Molnar from National Renewable Energy Lab presenting her work related to uncertainty visualization for ensemble data and surrogate models. So please take it away.
Thanks. Yeah. Glad to be here. Excited to talk to you all about this. So I just want to briefly set the stage here. We are kind of talking about a situation where we have run a bunch of simulations, computationally expensive simulations, where we run a bunch of inputs and we get a bunch of outputs. Here, the example I'll be using throughout the presentation is thinking about flooding from a dam break. So our inputs are information about how the dam breaks, and then our outputs are different variables about how the flood spreads. So here I'm showing an ensemble of contours of 30 minutes after the dam break, what the flood looks like at a particular location. So that's kind of our classic ensemble visualization situation. And now this is getting more complicated because we are also in this world where we have fast surrogates. So for example, we could train a surrogate model to learn the relationship between our input parameters and our output variables, for example, in SituNet. And what's nice about that is now we are no longer limited by where we have sampled for our ensemble. We now can sample anywhere in the space that is valid and that has validly trained our surrogate. And then we also can use these surrogates to go backwards. So instead of users just being able to define inputs, which is helpful, we can now enable users to define outputs, which could be more intuitive or useful for users that are not that have different backgrounds. So in this case, we could think about setting the output variable of how far the flood has spread in 30 minutes. So you could imagine having a widget here where you can drag and change that, and running an inverse surrogate. So either training a surrogate in the reverse direction, or you can use your forward surrogate essentially as a fast search tool to search through your input space in smart ways to find a set of inputs that could potentially produce the desired output. So with this complicated situation, we now find ourselves thinking about what are some of the challenges for uncertainty visualization to help us orient ourselves in the space and use these tools effectively. So we kind of came up, my co-authors and I, with 3 challenges that we saw as very important to think about. And the first is really, how do we use surrogates and ensembles together to leverage their strengths and mitigate their limitations? So as an example, we could think about our ensemble visualization really helping us see, well, there's clearly a partition in our data here. And we might be interested in thinking about this general location that is shown by the black lines. But without running more simulations, we can't get any more specific about where this partition might be. But we could use surrogates to query around this area to figure out potentially a better understanding of where this partition could be according to our surrogate, which is useful for thinking about quickly the shape of this partition, but also quickly understanding where we might want to query or run more simulations in the future. So the second kind of challenge that we are seeing is there's a lot of different uncertainties in this system that has ensemble data and surrogate models. So we have surrogates that can start producing and giving us a uncertainty quantification with the predictions. And we also have surrogates in the backwards direction that are producing actually discrete variables or discrete sets of inputs, and those uncertainties are different. And that's important to be able to communicate correctly. Lastly, I think with all of these kind of uncertainties and different relationships, it's important to consider that we might be showing things in such a way that a user might think this dashed line, for example, is a valid realization that could lead to their outputs, when in reality it's not. It's not maintaining this relationship where this middle input is inversely higher or lower as compared to the other inputs. So those are the three kind of challenges that we've been seeing in our work. Love to chat more with people here about that or offline. Yeah, and I want to thank my co-authors and also Hanwei Shen, who has been really helpful in this work, and then also our domain collaborator, Mustafa Altidakar. And yeah, I will take any questions now.
Yep, thanks for the great talk. I think this is really good position paper, you know. I I see that there are so many uncertainties when it comes to surrogate models and ensemble, and I thought about it, and there could be just one paper about identifying sources of uncertainties, you know, like and we could we could have some good discussion about it, but we have to move forward, and you might take some questions offline or later if we have some time at the end. Thanks.
Cool.
Yeah, next we have so next papers are honorable mention, so they are also really good quality, and all papers are good quality, but we thought these were also very special and unique. So next presenter is Chase Stokes from University of California, Berkeley.
Hi all, I want to thank you for your attention this morning. As he mentioned, my name is Chase Stokes. I'm a fourth-year PhD candidate at UC Berkeley. And today I'll be discussing kind of different modes of information. So looking beyond just visuals, you know, how do we express data uncertainty? So people often make decisions using uncertain data, and visualizations are a really key resource for those decisions. However, interpreting uncertainty visualizations can be kind of confusing sometimes. So things like the specific path of a forecast or the boundaries between risk areas can cause increased or decreased risk perceptions that aren't in line with actual likelihoods. So we can also communicate data through other modes of information. We can usually communicate data through text, and when doing so, we can use text-specific indicators of uncertainty like hedge words. We can also read this text aloud. So speech that is uncertain will include things like delays, pitch variations, and rate changes. And so I have a quick kind of demo for you there. So here would be a kind of certain speech example.
The most likely temperature low tonight is 34 degrees Fahrenheit.
Right, and then in contrast, here's the uncertain speech.
The most likely temperature low tonight might be around 34 degrees Fahrenheit.
Right, so you can kind of feel that uncertainty there, like 34 degrees Fahrenheit, right? So in order to examine decision-making under uncertainty, we examined a specific decision based on prior work. So salt lowers the freezing point of water, it causes ice to melt and prevents it from refreezing. And participants were put in charge of a fictional road maintenance company tasked with treating roads at or below 32 degrees Fahrenheit to prevent ice. In making this decision, they weighed the cost of salting, which had a $1,000 price tag, against the cost of damages, which was priced at $3,000. Based on this kind of cost-benefit analysis, we assessed the quality of the decision, the confidence in the decision, as well as the trust in the information provided using clarity, usefulness, and perceived accuracy of the forecast. We ran an initial study comparing these three modes of information and presented this work at Euroviz earlier this year. And in the original study, all of the forecasts were read by that same voice, the sort of Siri Alexa style that we heard earlier. One of the biggest follow-up questions that we got about this work was about the impact of the gender of the speaker. So shortly after Euroviz ended, we all hopped on a call and decided to address those questions. Based on the results from the prior work, we used a density plot as the visual information to show this kind of forecast of nighttime temperatures. The text forecast contained the same basic kind of information there, including some statistics and some description of skew. And in our prior work, we looked only at really unimodal representations, but we wanted to examine multimodality a little bit further. So we combined text and visualization, but we still wanted to make sure that participants were relying on the text to make the decision. So we actually removed the axis from the chart and just left the visual mark. Now, I know this display would not be used in practice, but by keeping the visual mark and not the axis, we can start to understand what's informative about combining text and visual information, right? Is it just the presence of the visual representation, or is it the ability to directly interpret that visualization? The speech condition also used the same visual mark, this time accompanied by an audio player. And we examined 6 different voices for this study. All of these are from Microsoft Azure, and I'll play a couple kind of examples to show the variation between voices, including those within the same gender.
The most likely temperature low tonight might be around.
All right, so that's one from the woman's side of things. And here's kind of another example there.
The most likely temperature low tonight might be around.
So you can see there's differences there in pitch, in rate of speaking, in kind of the pauses that they take. And I'll play one of the main examples as well.
The most likely temperature low tonight might be around.
So hopefully that kind of indicates a little bit of the sample that we were working with there. I'll go through our findings broadly and indicate when we were able to replicate findings from our original study. Around 200 participants from Prolific completed this study. And if you want further details on any of this, it's all in the paper. I'm happy to answer questions. We'll first look at the decision quality. So there were no differences between visual and text and an increase in risky decisions for speech. So these are decisions specifically where the participant should have salted the road, but chose not to, which is the worst decision from a public safety perspective. And this does replicate some of the results from the original study. We did not, though, find any effects of gender or any other kind of speech features either. Now let's look at how confident participants were in their decision. So text gave us lower confidence ratings overall in comparison to the speech conditions. However, this difference was not significant in comparison to the visualization condition. And so in prior work, the previous study, right, we did find differences between visual and text. And the main difference between that study and this one is that we included that visual mark in the text condition. So this may indicate that some of those, this kind of decreasing confidence can be addressed by providing a visual mark, even if they can't use that to directly interpret outcomes as they could with a visualization. However, the confidence was still decreased relevant to the speech conditions. And within the speech conditions, we actually observed no effect of gender, but a slight effect of normalized pitch. So higher pitched voices seem to instill higher confidence in decisions on average. No other differences, though, were present. I will turn to our final outcome, trust. And while the speech conditions did receive higher ratings of trust on average, this difference was not significant, and we didn't find any other consistent effects on trust either. This finding was not consistent with the first study, which suggested that speech would result in higher trust ratings. So it's possible this was affected the specific voice we used in the original study, or that this was affected by the inclusion of the visual mark. Now, so in some exploratory follow-up, we again kind of expanded the set of voices we examined. And in addition to including gender, we also examined 4 different accents, as well as a variant that was a child's voice with an American accent. We conducted some exploratory analysis, but we don't report any significance testing since we only had around 90 participants for a pretty large range of conditions. But we do compare it to the text and visual responses from our main study. So first, the risk associated with speech forecast was still higher than for text and visual. We also found some consistency for the impact of higher relative pitch on increased confidence. And we did find some difference in trust ratings for different accents, with Kenyan and Indian accents receiving slightly lower trust ratings than American and British accents. Overall, these results indicate a few interesting findings for communicating data uncertainty using different modes of information. So first, we should be aware that speech forecast of information may lead to a higher proportion of risky decisions. This is particularly relevant to data communication, as many weather forecasts are spoken over TV or radio, and so understanding that mode of information and how it impacts perceptions can be pretty critical. Additionally, it seems that most findings are consistent across gender and most variations in voice, with few consistent differences between voices across those different features of decision-making that we examined. However, there are possible impacts of other voice information, such as accent. We conducted some exploratory analysis on this and found that it may affect features like trust, and this definitely warrants some further exploration as well. There are many more details in the full paper, which you can read on my website. Thanks to my co-authors for their work on this project. I am currently seeking jobs based in the Chicagoland area, so if you are someone who's looking to fill a research role in Chicago, I'd be more than happy to chat further. And I also want to include a couple of resources for assisting the communities affected by both hurricanes over the past few weeks. I've included a Tampa-specific organization, but people still need aid and assistance kind of all across the Southeast United States. So there are those links for you. And thank you so much for your time. Happy to take any questions if we have time.
Yeah, thanks for the great talk. I really liked it. Never thought about, this additional evaluation of additional means of communicating uncertainty. Have you thought, just very quick question we're running already late, but have you thought about feeding these text descriptions to machine learning or natural language processing models, and maybe ML can help to give another prediction to reduce risk in decisions and stuff like that.
Yeah, I think it would be interesting to see kind of how to fit in the multimodal aspect of communicating data uncertainty into some of the kind of generative AI or machine learning that's going on right now. I think there's a very rich field for understanding how to present this information in these different modes. We only looked at one way of presenting it, so kind of other ways of describing uncertain information would definitely be of interest to kind of explore further.
Sure. Yeah, so there is also one more question on Slido, but please take it offline, sorry about
Sounds
that.
good.
So we
No
have to
problem.
move
Thank you very
forward.
much.
Yep, thank you. So next presenter is Laura Madzin from Sandia National Laboratory, talking about effects of number, order, and cost in multiple forecast visualizations. Please take it away. We can't hear you. Are you already speaking? You are muted.
Okay, can you hear me now?
Yeah, thanks.
Okay, sorry, Zoom was crashing on me. All right. Hopefully this will work now. Okay, are my slides visible as well?
Yeah, all good. Thanks.
Great. All right, so I'm going to be talking about multiple forecast visualizations, or MFVs. And in this project, we were looking at them in the context of electric grid operations, where this style of uncertainty visualization is very common. And right now, there are no principal design guidelines about things like how many forecasts to show. Should you show the extreme values, like the most extreme best and worst case scenarios in the forecast, or
I think we lost her. Maybe let's start with the next presentation, and then if she joins again, we can start back. So next presenter is Menjo from University of Utah, who will present about machine learning for surface box plot uncertainty visualization. Please go ahead. Thanks. Okay, she's back, but
yeah, maybe I can start.
Yeah, Laura, let's do your presentation after this, if that's fine. Thanks.
okay, sounds good.
We can't hear you, Minjo, or see your screen.
Oh, sorry, can you go next? I have some issue with sharing.
Okay, yeah, then let's go
Sorry.
back to Laura and we can come
Yeah.
back. So Laura, please carry on. Sorry.
No problem. Sorry, Zoom is acting up. Let me try sharing again. Okay, is that working?
I'm not able to see the screen yet, but
okay. Well, I'll just start talking. It says the screen share is loading.
Now I can see it. Now I can see it. Mock public safety power shutoff, right? So yeah, go ahead, please.
Okay, so this mock public safety power shutoff, we designed a task to mimic what
I'm not able to hear you, Laura.
No, we can't hear Laura.
Yeah. So let Menjo, are you ready, or do you want some more time? Otherwise, I will go with the last presentation. I have a recorded video. I can just play it and then you two can figure it out. So let's do that. Let me go ahead and share the video of last presentation by Gautam Hari. So you can send request. So I'm trying to send a request to share a video. Technician, can you please help? Matt, right? Sorry, can you please help us?
Sure, on it. You should be able to present now.
Yeah, okay, thanks. So let's see.
Should I try one more time? It keeps crashing.
Yeah, we are going with the last presentation first, and then we
Okay.
have a pre-recorded video of that, and then after that we'll do other.
Hello and welcome to our presentation about our filter, Fun M squared C. My name is Gautam Hari.
My name is Nurshad Joshi. There are three popular surfaces: isosurface for univariate data, fiber surface for bivariate data, and feature level sets for multivariate data. All three surfaces ignore inherent data uncertainty. Such neglection leads to misleading analysis. To mitigate adverse consequences of misinterpretation, uncertainty visualization is essential. Unfortunately, majority of uncertainty visualization algorithms are limited to univariate and bivariate data. The computation is time-consuming. If parallel algorithm is available, it is limited to library or architecture, and majority of uncertainty visualization algorithms are incompatible with visualization tools. Inspired by these challenges, we develop feature level set algorithms that are efficient, platform portable, and can be integrated with Parallel. This is how traditionally certain data is visualized. If data, which is presented as a red dot in this slide, is inside the user-defined trait, which is a green rectangle, then the probability is 1, else the probability is 0. However, you cannot visualize uncertain data with this approach. For uncertain data, in the closed form technique, we need to calculate the area of intersection, which is a blue square. We then divide the intersection area with user data area to calculate the probability.
This diagram shows our work in extending this computation to multivariate data. The diagram here specifically shows data with 3 variables. And to compute the uncertainty of this data, we find the intersection of the volumes of these cubes divided by the volume area of the data, which is a cube in red. As we extend this to 4, 5, and 6 variables and so on and so forth, this is simply a computation of an intersection of hypervolumes. We integrate these algorithms into VTKM so we could take advantage of parallelization across different architectures. Here is our filters at play. To the left is a full fidelity image of the DeepC impact dataset. In the middle is a mean field visualization with 2 times compression, and to the right is a uncertainty filter applied to the 2 times compression. We're able to show a more connected ribbing structure in the uncertainty filter here as compared to the mean field image in the center, which is a bit more closer to the original image on the left. Moving on to the Red Sea dataset, which is an ensemble dataset. Here we're specifically filtering for high temperature, and we're able to bring back some vortex positions here in the green square that were lost on the mean field visualization. It is important to note this is an ensemble dataset, so we don't have an original image to compare it to. We use a Frontier supercomputer to benchmark our data. It is an all AMD system, so we demonstrated our speedups with OpenMP and HIP. Starting with the DeepC impact dataset on the left, we show up to a 58 times speedup on HIP. Moving to the Red Sea dataset, which is larger, on the right, we're able to show up to a 64 times speedup on HIP. Now, if we take a look at increases in variable size, here we're demonstrating an increase from 3 to 4 variables with the colors orange and blue respectively representing them. We're able to find good speedups there as well on OpenMP and HIP, showing scalability. Here is our filters plugin into PairView, a production visualization tool. This plugin allows real-time data manipulation. Overall, we extended uncertainty filters to account and use multivariate data. We're able to show scalable performance as you increase in both dataset size and number of variables. And lastly, we integrated our work to VTKM and as a plugin, which can be easily used in PairView. But there's still work that needs to be done. Our current work is limited to uniform noise distributions. Now we want to extend this to Gaussian and histogram distributions as that is more common in scientific datasets. And our work is also limited to rectangular traits. We plan to extend this to polygonal traits in the future. Thank you, and we're ready for questions.
Right, thanks for the great talk. Since we do not have much time, I don't see any questions on Slido. So yeah, possibly we'll go ahead. You know, we are running out of time. But if there are any questions, please handle them offline. All right, thank you. Let's go next presentation. Yeah, Laura, please go ahead and try one more time. Thanks.
Okay, yeah, hopefully this will work. Okay. All right, so in our mock public safety power shutoff task, we were showing people the forecast of the wind speed over the next hour. And they were told they should shut down the electric grid if they thought the wind speed would go above 50 miles an hour. And so at the beginning of each trial, they saw only one wind speed forecast, but they could add up to 19 more by clicking a button to add one forecast at a time. And once they thought they had enough information to make their decision, they would decide whether to shut down the circuit or leave it on. And then they would see the outcome of the trial. So they would see what happened with the wind speed in that scenario. Here's a video of someone going through the task. They clicked on this add forecast button to add one forecast at a time. There were costs and penalties associated with their decisions. So each time they answered correctly, they got a 5-cent bonus. Each time they opted to shut down the electric circuit, they had to pay 2 cents. So that represented the cost of the protective action. But if they failed to take protective action and the wind speed went too high, then they had to pay a penalty of 10 cents. So that represented the hazard in this scenario. So in our stimuli, we had these sets of 20 wind speed forecasts with different shapes, and we manipulated what percentage of those forecasts crossed the critical threshold of 50 miles an hour. And based on our cost-benefit structure in the experiment, we could say behind the scenes there was an optimal decision. So if the percent of forecast crossing was 25% or lower, the optimal decision was to leave the circuit on. If it was 50% or higher, the optimal decision was to turn the circuit off. And our participants didn't know the optimal pattern, but this building this into the experiment allowed us to compare their performance to this optimal pattern. So we also had between subjects manipulations in this study. So we manipulated the order in which the first 3 forecasts were shown. So it could be random, or we might show the median or one of the extreme forecasts first. We also manipulated the forecast cost. So in one set of conditions, each additional forecast was free, and in another, people had to pay 1 cent for each additional forecast. So in terms of our results, looking first at the conditions where there was no cost to get additional information, we found that participants viewed significantly more forecasts when the outcome was more ambiguous. So in the 25 and 50% crossing conditions, which were on either side of our optimal decision boundary, people tended to view more forecasts in that case. But the forecast order had no effect on the number of forecasts viewed. It also had no effect on people's shutdown rates or how often they shut down the circuit. However, if we look at the cost conditions, we found that when we asked people to pay 1 cent for each additional forecast, they were very reluctant to do so, and usually guessed based on the first forecast they saw. And so even in cases where they would have made a much better decision and gotten higher bonus payments if they had paid a couple cents for more information, people didn't do that. And we found that when we made people pay for forecasts, there were significantly more suboptimal decisions. So for example, there were more cases where people turned the circuit off when they should have left it on. And most importantly, there were many more cases where people left the circuit on when they should have shut it down. So in this case, they're making a riskier decision. and incurring a penalty. So to summarize our findings, we found that people viewed more forecasts when the outcome was less clear, so they sought more information when they needed it. There were diminishing returns after seeing 5 to 6 forecasts. And interestingly, that's very consistent with prior work on COVID-19 forecasts using multiple forecast visualizations. In the cost conditions, we found that people tended to guess based on the first forecast, and this led to much poor performance and lower bonus payments. And importantly, the details of the experimental design made a big difference. So these experiments were done on Mechanical Turk. We are planning to run this task in the future with actual domain experts, so grid operators in this case. But within the Mechanical Turk context, this simple 1 cent cost really changed people's behavior. So in terms of recommendations for MFB design, we found in general that showing only one forecast can lead to suboptimal decision making. So representing the uncertainty with this type of visualization is useful, and something in the range of 5 to 6 forecasts might be optimal for supporting good decision making. And in general, in the context of electric grid operations, visualizing uncertainty is likely to help grid operators make more optimal decisions. Again, that's something we'll do more research on with domain experts in a couple months, but incorporating this into their existing workflows must be done very carefully. And thank you.
All right, thanks very much. I think I really like the talk. It's a different one. I just one very quick question. Do you think it showing like the best, like the minimum and maximum forecast is absolutely essential, like not just one forecast, but the user must be presented with at least minimum and maximum to get sense of the range, do you have any quick comment on that?
Right. In the conditions where people had the costs, so they viewed fewer forecasts, it was actually the random condition was actually better because people tended to be biased by seeing the extreme forecast first. But when they saw more forecasts, it didn't matter. So if they saw more than 3 or 4, the order didn't matter, and it didn't matter if the extremes were shown or not.
Okay. All right. Yeah, thanks very much. Please take any questions that are offline. I see there is one offline question, but please take it offline. So we are already reaching at the end of first session. So Menjo, please go ahead and
Sure.
sorry about everyone. Please bear with us for another 6 to 7 minutes. Yeah.
Hello, can you see my screen? Yes, good. Hello,
Yeah,
everyone.
looks good.
Yeah.
Looks good. Yeah.
Cool.
Thanks.
I will talk about our work, accelerated depth computation for surface box plot with deep learning. So this research was completed at the end of my PhD at the Ski Institute, University of Utah, in collaboration with Tushar, Jishan, and Chris. So let me start by introducing the concept of surface box plot. The surface box plot was introduced by Jensen and his collaborator in 2014, and it is a method for visualizing uncertainty in ensemble datasets. So specifically, they summarize 2D ensembles by ranking their members based on the volume depths. So each ensemble member is given a rank that reflects its depth relative to the others, allowing us to identify the most representative members or detect the outliers. However, calculating the depth for an ensemble involves 3 nested loops as shown in the figure, so meaning that computation increases cubically with the number of ensemble members. So this makes this impractical for use in visualization tools, especially when dealing with large or time-varying datasets. To tackle this challenges, we explore deep learning methods for predicting the depths. So our goal is to provide accurate prediction of depth order and enhance the overall performance. So in our approach, we use grid-based training samples, and each sample consists of data values from the ensemble members, along with the depth value used for calculate the training loss. So our neural network is built with multi-layer perceptrons using sign activation function and the sync mode activation at the final layer to ensure the predicted depth stays between 0 and 1. And the network inputs these data values and target the target depths and outputs the predicted depths. So now let's take a look at the results. So this table compares the predicted depth order against the ground truth using the RISE dataset, which includes 60 time steps and 50 members for each time step. So the rank preservation level reflects how closely our prediction align with the true order. So while there are occasional flips in order, particularly when ensemble members have nearly identical depths. For example, in time step 3, member 6 and member 48 differ by only 0.0002. So importantly, this local shuffle does not significantly affect the overall ranking. So overall, we found that our neural network accurately predicts the order and consistently identifies the median member. So to evaluate the performance, we compared our deep learning approach with the traditional method we talked about in the beginning. So we implemented the traditional algorithm in C++ and used TBV for parallel computation. When applied to the RISE dataset, our deep learning method achieves a 15 times speed up with GPU inference and a 6 times speed up with CPU inference. However, it's worth to noting that for smaller, like a one data set, our neural network performs slower than the traditional algorithm. To summarize, this is the first study applying deep learning neural networks to predict depth order for surface box plot calculation of time-varying ensemble data. So our prediction closely aligned with the ground truth, accurately identify medium members, which are very crucial for box plots. Moreover, the method offers a significant speed improvements, which enables the integration to visualization tools. So in the future, we aim to extend this work by exploring performance across more like diverse data size and ensemble data size. We also plan to investigate transfer learning for ensemble simulations, optimize the training process to reduce the training time, improve the model perception, and also integrate this neural network into the surface box plot visualization tools. Oh, thank you.
All right, thanks very much for this great talk. There is one question on slide 2. Why using machine learning? So quickly answer it because we are already running out of time. So by using machine learning, you essentially introduce uncertainty into uncertainty visualization tool. Is there a way you could introduce that visually?
Yeah, I think that's a very difficult question. So uncertain model, deep learning uncertainty for deep learning model is kind of like a very big topic now. So
Right.
I think yes, it's worth to explore like more about the uncertainty of the neural network and also
Right.
the uncertainty of the data visualization. Yeah.
Yeah, since I am the author on the paper, I know this stuff, so I can answer this question. The machine learning uncertainty works in this particular application of box plots because essentially our task is to find median member and outliers, and even if there is little bit of switch or uncertainty arising in the order of those, it doesn't it doesn't really change much the overall view of the data. So in our application it works, but this cannot be generalized to other applications. But yeah, anyway, thank you everyone. There is one more question. Sorry, I unfortunately cannot take it. Please answer that offline. Yeah, thanks everyone for joining the first session, and we are looking forward to next session also. We have panelists and some lightning talks and then capstone. So please join us at 10:15 sharp. Thank you. Thanks. Hello, everyone. Welcome back. Welcome back to the second session. So next, Deo Pagmar will oversee the lightning talk rounds, and then Chris Johnson will moderate the panel session, and we will conclude with a great capstone talk by Jessica Hillman. So we can start. Thanks.
Okay, so hopefully everybody had a nice break. We've got a total of 6 lightning talks set up, and for the speakers, we have a 90-second time, so please stay within that time limit. So the first one is a poster and by Patrick Petzold et al. So Patrick, go ahead.
Okay, hopefully you can see my screen. Hello, I'm Patrick. Today I present our web visualization and Python's UADA Pi. It is it is a joint work of David Hegler, Marina Evers, Daniel Weiskopf, and Oliver Dawson. The presence of uncertainty in data is ubiquitous. Uncertainty data.
We are not seeing your screen actually.
Oh, you're not seeing my screen?
Oh.
Okay, let's have a look.
Oh, team is
Okay.
able. I don't know. Maybe yeah, some issue on my end, but yeah.
Is it working now?
I can see it.
Okay,
Yeah, I
yeah.
can see it.
Please go ahead. I'm so sorry. It doesn't appear on my end. So yeah, but go ahead, please. Thanks.
Let's see, Patrick may have locked up. Are you there, Patrick?
I don't hear him.
Okay. Well, let's come back to Patrick at the end. So if we could we'll move on to the next. This is a full paper by Tajo Weremi. So Tajo.
Okay, hope you can see my screen. So in this work, we used polynomial interpolation to estimate uncertainty, errors, and visualize it. So typically, we have isosurfaces that are provided, as you can see, and these representations do not provide any insights about the uncertainty associated with the extraction process. And in this particular case, we can see that it's a bit different than the target isosurface. So first, we propose a method for estimating edge crossing errors, and we do validate our method with measured errors. Second, we show the variation between different interpolation methods, and that's to highlight the regions where we see more variation or significant variation between the interpolation in Martian cube. And second, we use derivatives to be able to identify hidden features and reconstruct them. And in this particular case, we can see that the feature reconstruction is able to connect the components that were disconnected. We did apply our method to some real-world data sets, and here we're showing estimated error and the variation between interpolation methods. And here we're looking at the bonsai data sets, and we're showing 2 possible isosurface reconstruction that are able to provide insights about the components that are connected and the ones that are disconnected. And that gives insights to the user on what may be the true surface or where the uncertainties are. Thank you.
All right, thank you. I failed to mention at the end of this session, we will we'll have a minute or two for questions. So if you have some questions, just chat them in the Slido while the talks are going on. Let's see. Okay, so the next we have a full paper by Shanu Soklani.
Hello everyone, today we are presenting our paper titled Uncertainty Informed Volume Visualization Using Implicit Neural Representation. In this work, we advocate for the usefulness and importance of using uncertainty-aware deep neural networks instead of deterministic neural networks for volume visualization tasks. While deterministic neural networks demonstrate excellent generalization ability, the absence of uncertainty information in the predicted visualization results can mislead scientists and affect decision making. Therefore, in this work, we employ uncertainty-aware deep neural networks and estimate prediction uncertainty using two deep uncertainty estimation techniques, the deep ensemble method and Monte Carlo dropout. This approach produces reliable, uncertainty-informed volume visualization results. We first learn the representation of volume data using an implicit neural network architecture with sinusoidal activation functions by using Monte Carlo dropout and deep ensemble methods. Then we reconstruct the volume data and estimate prediction uncertainty at each voxel. Finally, we generate volume visualization results and produce per pixel uncertainty map to convey the prediction uncertainty information along with the volume rendered images. Below, we show the comparison of the uncertainty and error map generated from the pressure field of Hurricane Isabel dataset, where the darker pixels indicate regions of high uncertainty and high error in each images. To know more about our work, please refer to our full paper. Thank you for listening, and I can take questions now.
Okay, thank you. So now we have a series of 3 short papers. The first one will be presented by Tajo again.
Right, hopefully you can see my screen. So in this particular work, we're proposing a new glyph design for vector field uncertainty. And showing 2 glyph designs that we use for vector field uncertainty. So we have a cone and a comet. The issue with this representation is that you are not able to distinguish the uncertainty that are embedded in the different components of the glyph. So this issue can be resolved by using the tail disk representation. And in this case, the uncertainty is embedded in the disk, and the size of the arrow and the direction represents the median direction. However, this representation is a bit ambiguous and is symmetric under rotation. So how can we improve this? So we propose the squid glyph, which uses super ellipses to better encode the representation. It removes the ambiguity and also provide a more accurate representation of the vector field uncertainty at each location. We did apply our method to different data sets. So here I'm showing an example with wildfire. And we can see that our method is able to better represent the uncertainty and is more accurate. It does not assume symmetry and is able to distinguish the different components and provide ultimately a better representation and more intuitive visualization for vector field uncertainty. Thank you.
Thank you. Okay, next we have a short paper by Robert Cisneros, and I believe we have a video for that Tushar will share.
Hello, everyone. In this work, we have uncertain data, ensemble simulations in our case, and want to create level set visualizations. From a previous work, we have an uncertain marching cubes implementation, which takes a data set along with an uncertainty model and returns a contour with a representation of per point uncertainty as entropy. We also started with a few relatively simple uncertainty models, but how do we develop or even evaluate such models? For instance, how many bins should we use when using a histogram to model uncertainty? We use entropy for this. While entropy may represent uncertainty, it may also just represent complexity or areas of interest. Therefore, we can't simply minimize this. We use the entire ensemble treated as an uncertainty model, which is the worst case scenario memory-wise, to gain the concept of a target entropy and to frame the evaluation as a trade-off between memory requirements and accuracy. We also created a model analogous to the histogram, where data is binned by in which quantile it fits. I'll quickly show results of these models on a 2D WIN dataset over a few contour values. When simply summing the per point entropy over the dataset, our full distribution model indeed provides a minimal across models entropy that we can use to evaluate model accuracy. The quantile model, orange here, has the nice property that more bins tends toward reduced entropy. So we finally get a sense of how to dial in the histogram model, blue here, and generally evaluate models regarding accuracy versus memory requirements. Please check out our paper for additional results, including some control tests where we created ensembles with random noise, as well as tests on a larger 3D Red Sea dataset. You can also find some more subtle discussions regarding the use of entropy and a few counterintuitive results. Thanks.
Okay, and the final short paper will be presented by Jishen Li.
Hello everyone, today I will introduce our interface for visualizing uncertainties in ensemble wildfire simulations. We designed and implemented an interactive visualization system for visualizing ensemble wildfire. We use contour box plots as a key component to summarize trends and variations of the spatial patterns of firefront contours. In this example, the contour box plot shows large contour variation in the wind direction and terrain with a positive slope. Variation indicates that the location of the firefront is very sensitive to the wind and the slope of terrain, which align with our domain experts' hypothesis. Contour band depths also provide hints about the simulation's outliers. In this example, we identify 3 instances of unusually low contour band depths. We identify an abnormal amount of south wind caused by numerical instability. In addition, we provided a visualization that allows users to overview changes in time and select interesting times. We also enable users to choose a point in the space and examine the firefront arrival time of different simulations. In the future, we aim to extend our work to test different visual encodings of uncertainty and address different types of uncertainties. Thank you.
Okay, thank you. And then Patrick, let's circle back to you and see if...
Yeah, let's hope it works now. Look. Okay. Can you see my screen now?
It's yes.
Okay, now, great. So hello, I'm Patrick. Today I will present our uncertainty-aware visualization Python toolbox UADA Prime. It is joint work of David Hegler, Marina Evers, Daniel Weiskopf, and Oliver Dawson. The presence of uncertainty in data is ubiquitous. We propose a data analysis and visualization framework that supports uncertain data in all stages of the visualization pipeline. At first, we model the given data as probability distributions, apply various transformations, especially tailored for uncertain data, like uncertainty-aware PCA or uncertainty-aware MDS to it. To display these distributions, our framework supports various 1, 2, and higher dimensional visualization techniques. Many commonly used plotting libraries and data analysis libraries such as Matplotlib or SciPy offer a plethora of tools, but these are all not tailored to be applied to uncertain data. Thus, a collection of easily accessible, uncertainty-aware data transformation and visualization algorithms is missing. Thus, our proposed framework implements these uncertainty-aware algorithms and acts as a foundation for researchers to develop new uncertainty-aware algorithms and directly integrate them. Here you can see a small example how our library is called and transforms high-dimensional data to 2D and displays it. Thank you for your attention.
All right, thank you. And thanks to all of the presenters in this session. If there are any questions, please put them in the Slido. I had one quick question for Tajo on the glyphs. One of the problems with glyphs is visual clutter. Did you look at the at the associated clutter with these new types of glyphs for looking at vector fields, and any comments or experience with that?
Sorry, you're muted, are you? Or yeah, we can't hear you.
Okay, can you hear me now?
Yes.
Okay, sorry, my computer just acted up. I don't know why. Yeah, we did think about it, and that's something we're planning to explore for future work. And that is definitely an issue when we're looking at large data sets. And for now, what we're looking at in our interface, we provided like selecting a region, taking a slice to be able to reduce clutter, and also downsampling. But I think the next step we're looking at is how can we actually design something that we able to downsample and visualize the uncertainty of the downsampling part, but also the uncertainty of the actual data sets in it. And also there is a performance issue that will come with that when we're looking at the large data set. So yeah, we are looking into exploring it. A clear answer, we don't have it yet, but that's something hopefully by next year there will be something that we have that address this issue.
Great, thank you. All right, well, thanks again to all of the authors in this section, and thank you for your wonderful paper. So turn the time back to Tushar.
All right, thanks everyone. So next session is panel session. Very excited about it, and Chris Johnson is going to moderate that. So it's going to be a very interesting discussion. So Chris, please take it away. Thanks.
All right, thanks, Tushar. Good morning, everyone, and let me welcome our panelists. We have Hanwei Shen, we have Matthew Kay, Lace Padilla, and Garrick Schuerman. And we're going to have a discussion about uncertainty and uncertainty visualization. Because of the short time, we're not going to have like slides where everybody presents slides. We're going to ask some questions and have the panelists answer and hopefully have some discussion. So the first question to the panelists is, for visualization, what are the main uses for showing uncertainty? Is it for reliability, for more trustworthy communication? Is it for discovery? What do you think are the main reasons that we want to do uncertainty visualization? Let's start with Hanwei. What do you think?
I think, Chris. So I've been working on machine learning for Sybase for the past 5-6 years, right? So obviously, I think really the use of AI in visualization and also scientific analysis is still very limited. And one main reason is they don't believe. I mean, the scientists, they all have some kind of doubt about, using inference to predict the output for a ensemble parameter. So the use of uncertainty is really just, a way to gain their trust. So trustworthiness from the scientists, right? They need to know the errors. They need to know how certain you are. And they also need to know how are the machine learning model works, right? So this is actually why for the past 3 years, I've been working with my student. And this is actually a pretty challenging problem. This is actually equally challenging as explainable AI, right? You want to explain how AI works, but you also want to explain the uncertainty. So that's, I think this is going to be, as long as people are working on AI model, this problem will never go away. So this is what I think, the use of uncertainty.
All right, thanks, Lace. So do you think that it's all about trust? And is uncertainty visualization going to help us convey trust to the users? What do you think?
So I think trust is tricky, and I think that conveying trust shouldn't necessarily be our goal, but helping people calibrate their trust to the level of accuracy of a particular model, I think should be the goal. So I think with that, it's important to note that people assume that there's uncertainty in any type of model or data, any type of future prediction. However, the way that they assume that or imagine the uncertainty in their mind is inconsistent across people. So by displaying and quantifying the uncertainty, we can ground their assumptions about uncertainty in the actual data. So I think that's important to note across all different user types, that by displaying the uncertainty, we are anchoring them in some type of reality versus their mental imagining.
Right.
Throwing it
Matthew,
over
what
to
do you
Matt.
think? Yeah, Matthew, what do you think about
I think like I'm really glad Lace brought up the idea of calibration, because I think that is a lot of what it's about. It's calibrating the trust to the actual uncertainty. And I think like part of what that serves is trying to help people make better decisions, right? I think especially on the empirical side, we've seen a lot of people starting to move in that direction in terms of valuation of uncertainty visualization, is looking at things like decision quality. And I think that kind of stuff is pretty important. Like I don't really care if people can reproduce numerically a probability so much as I can observe that the decisions that they make like show me that internally they are acting on the probability I want them to act on, whether or not they can reproduce that number. And so I think that's kind of where I think about uncertainty visualization, is trying to help people make better decisions.
So Garrick, what do you think? Is it all about making better decisions, or can it help people better understand their data and discovery? What do you think?
Yeah, so my central point is basically avoid mistakes. So if you are in a data-driven discovery process, we studied this with climate simulations, ensemble data, then you may say, okay, there's some shift of some pressure system that may be important for Europe in our case. And then you want to compare that to a baseline. Once you understand there's uncertainties, that there is a certain statistics underneath, you really want to see if you're currently really significantly different. You also want to avoid, and we had the decision making, I think Matthew brought that up, and Lace as well. You want to avoid making decisions that are not backed by the data. Yeah? If you have different interpretations, which may be present in an ensemble due to uncertainty there, and the data variation is too high, then for data discovery or data-driven discovery, but also for making decisions, you want to back up. It's of course not easy to communicate that, especially to people, and this is what Lace was referring to. If people are not well trained understanding, let's say, making good decisions based on something that's inherently uncertain to some degree, right? Yeah, you want to get certain about something to make the best decision, to really be sure I found a discovery. Yeah, you know that in physics, Chris, much better. Yeah, they want to have like CERN 4 or 5 times the usual variation in the discovery to make sure that they didn't do something wrong. I think the main point for me is really there, help people making good decisions backed by the data, or discoveries backed by the data, knowing that it's not perfect what you have.
I liked one of your phrases that I hadn't heard before, being certain about the uncertainty visualization. So Lace, tell us about, what do you think about the effective communication of uncertainty and the challenges of conveying that uncertainty to, I guess, both a scientific audience and perhaps also a even more challenging, maybe a general audience?
I think that's very challenging. And I think the really tricky part is that there's no one size fits all solution. So the right type of visualization is going to vary based on your users and the data and the task that you want them to do. And I think maybe the frustrating part as a practitioner in reading, many of our papers is that oftentimes we say you need to do some type of evaluation to determine if the visualization you're working with, in fact, does support users. Because oftentimes we find unexpected results within the research. So I think understanding the nuances corresponding with when a visualization is likely to be successful or not, and understanding when those edge cases exist is very challenging without experimentation, because often the results are unintuitive. And that unfortunately is unsatisfying if you're not actively doing research. But I think that's the current state of the field, that we can't just say everyone should go out there using, X visualization method. That's not where we're at right now.
So Matthew, what do you think?
Yeah, I mean, I agree. I think I mean, so to Lace's last point, I have this sort of continual experience of seeing, okay, here's a visual encoding, works well in this domain, you move it to this other domain, and now there's this new misinterpretation that people have, right? I think like the easiest example of this, without, trying to like gesture and create visualizations in all of your minds. Um, if you think about something like a uncertainty band around like a regression, right? That's essentially the same visual encoding as say like a hurricane error cone. Hurricane error cone is a band on a map where we normally have these sort of spatial associations, right? Bigger things are bigger. And so then you have these misinterpretations, like 30% of people will misinterpret that cone as telling you the forecasted size of the hurricane when obviously it's not, right? And so I think it's just this like I don't foresee a way in which we have a sort of like overarching model that allows us to say, oh, this uncertainty visualization will be the best for this situation, because it always is complicated by the background knowledge that people bring to it or the other associations people have with a visual form in a particular context. And so it's just more complicated than that, unfortunately.
Hanwei, what do you think?
Okay, yeah. So well, I think you can never be certain about uncertainty. So actually, I want to brought in the important thing is how are you going to bring human into the whole decision loop, right? Because when I say you can never be certain, it's equal to like you can never be certain what people are thinking, right? So I actually, this is actually why I work with Sam, who just presented a short paper about user interface, right? You don't just present uncertainty to the people. You actually want to allow them to be able to do something with it, right? So and in a way that developing a natural user interface, and you might even want to observe how they are doing with the uncertainty, it's going to be key. Otherwise, I kind of feel that to me, a very simple-minded person in SciViz, a lot of visual representation has been pretty effective, like a contour box plot and all that, right? But the thing is, those should not be static image. They should be something that user can do with it. But what to do with it, that's actually a bigger question. That's my view. Yeah.
So Garrett, one of our colleagues in geography, Alan McCachran, to follow up on this conversation, when he was looking at geography and trying to assess people's understanding of uncertainty, his view was that more was not better, and that it was he basically said, well, you should say you have a low amount of uncertainty or you have a high amount of uncertainty, and if you try and do much more than that, you'll just confuse people. And maybe if they're really sophisticated, you could also have a medium amount of uncertainty. But that his view was that it was too easy to confuse people, and we should just have like the minimal descriptions of uncertainty. What do you think about that?
Yeah, I see the point, but I'm still not happy with it, right? If you say low or high uncertainty, there are scenarios. Let's take Matthew's example of a hurricane, right? Because we all are kind of affected right now from it. So if there is not just a small variation in the track it may take, but there is one scenario where it goes over Florida and another one where it hits Louisiana, then you want to show both. Otherwise, if you say there's a low or high uncertainty, you're really close to saying basically I have this mean idea, what's going to happen, and I'm more or less certain about it. But if there are two, in a simple case, right, distinct, quite likely scenarios, which are quite different in terms of how they affect people, what kind of decisions I have to make. I have to convey that somehow. On the other hand, I fully agree with all the others. It depends on the audience. We are looking at the cognitive process already if we convey, we're mostly discussing right now scientific information. And uncertainty is not making it easier. It may make it more precise and obvious there what we don't know or the variation, but I think there are cases where it's okay to say I'm not completely certain, but then the question is, what do you do with it? Yeah. If this is knowledge discovery, okay, you have to do more analysis, more data. If you have to make a decision about where to evacuate people, you don't have the time for that. You have to still make a decision. And if there are 2 different scenarios or 3, then you have to show all 3, even if more is difficult then. But you cannot just ignore them and say it's going over Florida, but we're highly uncertain about it. That's not going to help, right? Yeah, for making a time critical decision.
So,
So
Leish, what
just
do you
to,
think?
well, Matthew and I actually had a paper where we gave people, in addition to visual representations of uncertainty, we told people that within that prediction, there was high, medium, and low uncertainty around that estimate. And it turns out people can, they kind of bias their estimate towards the direction that we said. So if we said there's high uncertainty, they tended to make more risk averse decisions. And if we told them it was more certain, they tended to update a little bit. Now, there's a lot of ambiguity in terms of language use, which is why I think Chase's talk was really cool, describing, looking more into the language description of uncertainty. But I think it kind of comes to a broader point for me, which is that I think in certain contexts, you don't necessarily have the luxury of showing these high fidelity, beautiful, sometimes interactive visualizations. If you're truly looking at hurricane evacuation, sometimes people are getting a text message on their phone, for example. So we need ways to communicate that in low fidelity situations. And maybe all we can say is that there's high, medium, and low uncertainty around if you're needing to evacuate. So I think we need the capacity to scale what we're communicating to the specific needs in the specific context. And I think that's been very much understudied. We don't totally know the right way to do that.
What do you think, Matthew? You want to follow up on that?
Yeah, well, I agree with everything that Lace and Garrick just said. I think that I'm a lot more optimistic that we can create uncertainty visualizations that convey a little bit more, at least in the context, like Lay says, when we have the capacity to, right? I mean, I think that some of the work, I guess to me this comes back to like there's sort of work in psychology that says, oh, people are terrible at making decisions, they have all these heuristics and biases and whatever. And I think that's like one perspective on it. And I think a different perspective on it is the more like HCI perspective, which is like, actually, we're not that bad at making decisions, right? I mean, as a species, we've gotten pretty far at making some pretty tough decisions under uncertainty to get us to the point that we are now as a society, and with the like crazy things that we can do. Maybe it's just like the way that we're communicating these things that makes it difficult for people to make good decisions, right? I mean, I think a lot of the classic heuristics and biases literature is like, a textual description in a kind of roughly described scenario, read this paragraph and then make a decision. And then often people make bad decisions, but that's like not the way we make decisions in the real world. It's also not the way that we experience things in the real world, right? I think if you put people into real decision-making scenarios, you give them representations that work the way that we think, you can actually have them make pretty good decisions. And that's something that I think we have seen a little bit in the uncertainty visualization literature more recently, where we're trying to do that.
So to you, Hanwei, to follow up on that, a lot of at least for the uncertainty visualization for scientific applications is in the language of probability and statistics, which I think that many people, including some scientists, don't have a good grasp of, let alone the general public. So how do we maybe overcome that, or can we, or what do you think are there ways that we can better either teach or educate people about probability and statistics, or should we, like what Matthew has indicated, maybe we should figure out ways to better change our visualizations to how people make decisions in the real world?
Yeah, so actually to me, most of the scientists I work with, they have reasonable grasp about probability, right? Because this is a part of mathematics and statistics, right? I think what they don't know is what do you mean by 85% this value is correct, right? Like what is the 15% you haven't shown me, right? So to me, to bridge the gap is, 85% give them some kind of confidence, but then we probably also need to show them the 15%. From a scientific simulation point of view, I would say you want to show different scenarios, right? This is actually where I feel generative AI can really help, right? Because if we have one single set of simulation data, you say, hey, this isosurface is so uncertain, but then they will say, well, tell me what is certain, right? Then you have to generate something that tell them, hey, this is certain. So I would just, this is something me and my student we've been working on, is to how can generative AI help to produce scenario that they get a very firmer grasp about what is going to happen. Yeah, so this is what I think. And then also back to your question, Chris, about comment about this, more uncertainty is not necessarily better. So I actually agree with it, because really, at least from scientific simulation, to predict when the fly is going to come to Tampa, just show them 85% is not that what they want. They want to see is what decision I need to make to reduce the uncertainty of something. And for example, you don't want to fly to Tampa and straight in the airport, right? So I think there should be like a data generation, uncertainty visualization and the prediction, also to improve the data source, right? Like, okay, given a different scenario, and then once you have a scenario, they make decision, they can immediately see the feedback about now what is the uncertainty left, right? Because we want to predict the climate, right? We don't want to know the uncertainty of the climate. We want to know what's going to happen. So I think it's really should be a loop, a closed loop. So I agree with you. More uncertainty to scientists, they're not going to feel any better. So we need to help them to reduce the uncertainty. Yeah, but that need to be a loop as opposed to just predict and without saying anything more. That's my take.
So for the last question I'll ask, and we might have a little bit of time to open up for other people. So if people think about a question you want to ask the panelists. So my last question will be, so what do you think is either you can say what you're working on, or what do you think is one of the most important areas of research that needs to be tackled in the area of uncertainty visualization, which you very well may be working on. So Garrick, what do you think about a research challenge that's still unmet in uncertainty visualization?
I already was mentioning two, and one is if there is uncertainty, then look at the probability, but try to communicate if there are different scenarios, not just unimodal distribution, you would say, and how can I communicate this? I think we still also have to do a lot, and we saw this a little bit in Daniel's keynote this morning, how to really process uncertainty to our pipeline. These are two things. There's a lot more about the communication, but I'm sure some of the others will focus a little bit more on this. So I stay with this too.
All right, Lace, what are you thinking?
I think for me, we're going to work on this a little bit, but this is more of a call to action. And I think one of the biggest challenges is studying uncertainty and decision-making in naturalistic contexts, outside of the lab, outside of these very kind of clinical environments that we create. And part of the reason it's not done is because it's frankly really hard to do. So I would love to see more work that sincerely tries to look at people in how they're making their decisions, in which ways, in the types of visualizations that they're engaging with naturally. And yeah, I hope someone in this call or watching Zoom gets inspired and takes on that challenge.
Matthew, what's your top research challenge?
I like that challenge. I mean, we've been running studies on people looking at election forecasts during US elections for the past couple of years. We're doing it again this year, which is freaking insane, basically, and very difficult. So yeah, I think that's a big challenge. I think that I really liked Daniel's sort of call to action with the pipeline stuff. I've been thinking a lot of, a lot of the people that I work with who are more on the data science side are people who are building models using probabilistic programming languages. And like my ideal world is where you can get all the way from a probabilistic programming language into something like the grammar of graphics without leaving the probabilistic programming abstraction. And so I've been building tools to try to do that for a couple of years. And the last thing that I'll say that I think is really big on the communicating decision-making side is communicating multiple levels of uncertainty simultaneously. Things like uncertainty in probabilities or the sort of qualitative uncertainty stuff, the study that Lace was talking about earlier that we did. I think that's really hard. I think we don't really have a good grasp on how people interpret any of those types of representations or how they make decisions from them. So yeah, I think that's a big challenge too.
All right, Hanwei, what's one of your top research challenges?
Okay, so I will have two. One I will do it, the other I will let you to do it. So I'm because of machine learning just really so popular. So I have been working with my student on quantifying uncertainty, which is generating uncertainty data such that you can visualize it. So I will let you guys and other researchers work on, hey, once we generate the uncertainty, how are you going to design a better visual coding to help people do it? And also, I recently joined NSF as a program director for human-centered computing. So I want you guys to help and propose, hey, how can you bring human into this uncertainty quantification decision making? Because obviously I cannot find my own research, right? So I will later not do it. I will let you guys do this human part of it and teach me how we can utilize uncertainty model by mathematician and statistician. So those two major challenges. I will do one, the rest will give it to you guys to do it. Thank you.
All right. So we have one question on Slido, which says, loving this conversation. How do you think we can improve the communication of data uncertainty to broad audiences who may lack foundations in statistics? So let's move to the general audience. All those, New York Times and other newspaper plots that may or may not have any uncertainty. How do you communicate effectively to a general audience? Who wants to take that? Yes, Garrick.
Yeah, so I suggest, as before, to try, if you have different possibilities, just show them one in a second scenario, something like that. Yes, it can be like this, or it may be like this. If it's just one, then your idea of basically showing the most likely event, if more or less all predictions are around that, then show them this. If it's about decision making, we had that before, then just basically give them the most likely decision. Leave now, or it's dangerous, even with a small risk of being wrong. But yeah, just say, okay, you probably understand the clear message, so I may give you 2 instead of 1 because we are not sure, but hiding all these probability stuff.
Anyone else want to follow up?
You go. I want Matt to go.
I mean, I think simplifying is good. I think that part of what I've seen, especially from the stuff we've been doing more recently on election forecasting visualization, is you have different sorts of audiences depending on people's education level, or like Lace had a nice study looking at working memory capacity. I think that's where you start to see differences in effectiveness of different encodings, where to me, I think about how do you design a display so that there is this like top line note, which is kind of what Garrick is talking about, right? And maybe that's what's the most likely thing or the most likely couple of things. And maybe you communicate the uncertainty there in kind of like a frequency way, right? So it's like, oh, there's like a 9 out of 10 chance that this is going to happen, right? Really rough resolution, frequency framing instead of probability framing. And then you also, I think, even for that broad audience, there's going to be, a good number of people, probably about half of them, who still want more information, and that additional information is going to gain their trust. And so that's where you have something else that maybe shows a little bit more detail, like a probability distribution in some representation, like a density or dot plot or CDF or whatever, right? Or, some more complex representation than that.
All right, well, we're out of time, so let me please join me in thanking the panelists for a very interesting discussion. Thank you, panelists.
Thank you. Thank you, Chris.
So I'll turn it over to Christy to introduce our capstone speaker.
Hi again, everyone. I am very excited to introduce Jessica Holman. She is a researcher at Northwestern University and has been working in this area for a very long time with lots and lots of best papers and very influential work that I personally am always looking at what she's doing every year to keep track of what is going on. I really appreciate her approach to the problems that we look at here in the uncertainty viz field. And so I'm very excited that she agreed to join us today. So Jessica, I'll turn it over to you. Thanks so much again.
Sure, yeah, thank you for having me. Let me just share my screen. So you can see my slides. Great. Can someone confirm they're seeing my slides now?
Yes.
Okay, great. So yeah, thank you so much for inviting me. I remember one of my first Viz conferences, I went to an Uncertainty Viz workshop, might have been organized by some of the same people here. So it's quite an honor to be asked now to give a capstone at one. So I'm calling my talk, "The Meaning of Quantified Uncertainty is Its Use." And this sort of implies a question, what's the meaning of quantified uncertainty to some task? And I think about this question a lot. As it relates to this workshop, another way we could think about this is, what's the value of a better uncertainty visualization? And so, we can think about this question in all throughout the statistical modeling pipeline. So it comes up in discovery, where we might care about, what's the value of better representations of variance to tasks like exploratory data analysis. It comes up in hypothesis testing, where we might ask, if we're doing causal inference or presenting some causal effect, what's the best way to visualize that information? And it comes up as well in predictive modeling, where I might have some machine learning model making predictions, and I know there's predictive uncertainty that I should convey. And so I guess one way we could think about understanding the value of better uncertainty visualization is through empirical study. And I think this is probably sort of the default that we often think about if we were asked this question, what's the value of a better uncertainty visualization? And I think we would all probably agree that an uncertainty visualization as an area, empirical work is really thriving. So over the last 5 or 6 years, there have been many awarded papers that are really about uncertainty visualization. There's consistently been uncertainty visualization sessions at Viz. There's been workshops like this. And so I think, we're doing very well when it comes to finding ways to design studies that show differences empirically between different visualizations. But another way that we could try to understand the value of better uncertainty visualization is using theory. And this is because, when we're talking about uncertainty, we really can rely on statistical theory because we're talking about statistical constructs typically. And so the message of my talk, what I hope to convince you of today, is that theoretical analysis or theoretical justification should play a bigger role in how we do uncertainty visualization. And this is because it has this key role in how we evaluate what we're seeing when it comes to use of some uncertainty visualization. So I think we're sort of hampering progress by relying only on empirical research. And one reason why I think empirical study results cannot give us the full picture when it comes to the value of better uncertainty visualization is because often when we do an experiment and we present the results, there's still important sources of ambiguity that we cannot resolve. And so today in my talk, I'll try to walk through and give you a sense of what I mean by these ambiguities and how a theoretically founded approach that's going to be based in a rational agent perspective could help us here. So most of the empirical studies, I think, or the sort of gold standard empirical studies are going to, ask what's the effect of some different uncertainty visualizations for some task, which might be an inference task, it might be a decision task. The gold standard would be to actually run a controlled experiment where you're going to randomly assign visualization types to people and see how they rank in terms of error or some other performance measure. So, for example, maybe I want to see which way of visualizing uncertainty in a temperature forecast that's showing the daily low expected temperature is going to lead to the best decisions under uncertainty, where my task might be something like I'm asking participants to imagine that they're a city planner and they have to make a decision conditional on the temperature about whether to salt the roads or not. So I show them, maybe mean and confidence interval. I might show them a gradient plot. I might show them a hypothetical outcome plot. And, I want to rank the displays, and that's going to give me insight into what's the better uncertainty visualization. And so, in any given study, I have to generate some data. I have to make the visualizations. I'm going to then, give the person the decision task that I've come up with. In this case, do you want to salt the roads? And I have to compare performance along some scale. And so, often we might see accuracy in a study, but we can also be a little more sophisticated. And in some studies, we might, penalize different types of errors differently. So maybe I'm going to say that the worst type of error in this road salting task is a false negative, because if you don't salt and then it freezes, like people might get in accidents. Slightly better than this, or not as bad, would be a false positive. So, so this is kind of, a canonical study, let's say, that I'm going to use as an example. And so the aspiration when we do empirical studies like this to get insights into how different uncertainty visualizations compare is that we want to go from these specific experimental settings that we're studying to more general sort of design guidelines. We want to run our study. We want to choose our decision task in a way that is going to allow us ideally to generalize to sort of some larger class of situations, so that we can say, in our study, we found that the gradient plot was the best performing visualization. Therefore, we should use gradient plots in all of these kinds of decision studies. And so this is where I think we run into problems. And one of the problems is that, the way that we typically, or where we typically stop when it comes to presenting our results and making sense of those results, leaves a lot sort of unresolved. So let's think about what we still don't know from a typical presentation of experiment results that might look like this. So here, on the y-axis, I have my performance measure. This is this average score given the scoring rule that I've already showed you. It could be accuracy. It could be whatever you've used in your study. I am seeing, the performance of different conditions. And here I might see that the gradient plot is looking noticeably better. And, I might see also when I run my statistical test that this is a significant difference. But it's hard to make sense of this. If you stop and think about it, what does this really tell me? Well, without knowing much about this particular problem, it's hard for me to say, how much does this difference matter? How much better are gradient plots really? And is this likely to matter in practice? And one reason why it's hard to answer these kinds of questions from the typical results presentation is that we don't really know much about how good or bad performance could feasibly be in the study that we've run. So imagine that I could tell you that the upper bound of anyone's score in this study, the best score anyone could possibly get is over 1,000. And some dumb strategy that doesn't even rely much on the visualizations could get you about 20 or less than 100 as a score. if this was the case, then if you looked at these results, you might notice that this difference between, the gradient plot and the next best plot is a very small percentage of this total space of, performances that we might see in this study. And all of the visualizations looks like are not doing much better than the stupid lower bound where, we're not even heavily looking or relying on the visualization. So if we knew this, we might take the same experiment results I showed you on the last slide and conclude something very different, which is that all of these visualizations are bad. We have a lot of work to do. Maybe we're not even focusing on the right thing. Maybe it's not the visualization that matters. Maybe we're giving people the wrong information. On the other hand, if I showed you, or if we found that the upper bound, the best attainable performance, is not much higher than how these visualizations are doing in our empirical results, then we still might conclude that this difference doesn't really matter between gradient plots and other plots. But this time it's because all the options are good. They're all getting at least 90% of the best possible or upper bound performance. And finally, I think what we often assume, the situation we assume we're in is closer to this one. So perhaps the upper bound and the lower bound, are fairly close. And this percentage, this difference that I see between the visualizations is actually a big chunk of this possible range of scores. Then we actually do care about this visualization difference. Then we know that the visualization choice itself appears to have some impact. The problem is that, we, I think, often assume that we're in a setting where the visualization choice, is a big determinant of performance, but we actually don't know which setting we're in. Of the few that I just showed you, this is what's ambiguous. We don't really know which paradigm we're in. And so what I want to present today is an approach that is based in Bayesian decision theory, which allows us to really disambiguate sort of what we're finding from empirical studies by figuring out what's the best attainable performance and what are other reasonable baselines for understanding what's possible in the decision problem that we've induced by running an experiment. So what we're going to do is use the expected performance of a rational agent on the same experiment that we've given to human participants, or that we're going to give to human participants if we haven't run it yet. And we're going to then compare the expected performance or expected score of this rational agent to the scores that we see from actual human participants or behavioral agents. So let me walk you through in a moment what the rational agent, what this actually means. What do I mean by a rational agent? How are they actually, doing the experiment? But first, just to give you a sense of what we want to get out of this analysis, we want to be able to calculate this upper bound. So we're going to take this rational agent and we want to know the best attainable performance in our experiment. And so we define a rational upper bound, which is going to be the expected score of this rational agent who has access to the visualization, who knows something as well about the experiment task. For instance, they know the prior. And this is going to define the best possible performance of any human in our experiment. And that's going to help us interpret things. Similarly, we want to define a lower bound. So we want to take the rational agent, and now we can think about, well, what would be a dumb strategy that we would, hope would not do super well compared to the upper bound that would not even involve the visualization. And so we can imagine a rational agent who knows something about the experiment. They know, for instance, the prior, but they don't even get to access the visualization. So we're going to simulate the performance of a rational agent without access to the visualization and compute the expected score on a random trial this way. And so what this corresponds to then is, having someone in our experiment who maybe knows something about the prior, the best choice, the best choice, if you don't actually get to see the individual visualizations, and they're just going to have to pick the best fixed action across every trial we give them. So that's what this lower bound is going to represent. Okay, so once we have bounded the performance that's possible in our experiment, what this gives us is a way of quantifying the value of information. So again, the question I started with is, what's the value of quantified uncertainty, or what's the value of a better uncertainty visualization? And we can use this value of information to sort of get a sense of sort of the maximum possible lift one could get in doing the experiment if they have access to the visualizations versus they don't have access to the visualizations. So we would hope this is big, right? We want to see that there's a lot of room for the visualizations to improve decision performance. We can use this here, this value 2.27 is just an example. This is in the unit of the score. So whatever we're scoring rule we're using to gauge performance, that's the unit that we're seeing here. And what's useful about this span is that we can use it as a normalizing unit to talk about different, visualization conditions and how much of the possible lift from having the visualization different conditions are actually getting when we run them with human participants. So we'll use this as sort of a normalization tool. So this is all kind of high level. So I've tried to give you an intuition for what we're going to do with this rational agent. But now let me walk through in a little more detail how we're getting these bounds. And you don't have to follow everything I say on the next few slides, but just keep in mind that what I'm going to do here is basically sort of formulate the task that we're going to use in some experiment in statistical decision theory, and then think about how a rational agent would solve that task. And, one thing to keep in mind is that, this kind of approach, even if you have not designed your study with sort of the idea of statistical decision theory in mind, this kind of approach can still apply. So you can imagine that I'm sort of picking up an arbitrary visualization study from the literature, and I want to understand and analyze the decision problem and find these bounds. And so this approach that I'll show you is meant to do that. So first we have to formulate the decision task. So anytime we do an experiment, we're sort of inducing a decision problem. And a decision problem first needs a payoff relevant state. So basically we're talking about decision making under uncertainty, usually when we're concerned with uncertainty visualization. And so in this example experiment, the payoff relevant state is whether it freezes or not. That's, the quality of my decision in the experiment depends in part on this state. We also have to have a data generating model. And so this is just the way that we're going to generate the data sets that we're later going to visualize to make our stimuli. And so we can imagine in my forecast example, say I have temperature distributions. I'm going to make sure my temperature distributions are normally distributed, perhaps. I'm going to fix the mean. So the mean temperature is always going to be the same, and it's going to be 5 degrees Celsius. And I'm going to vary the standard deviation, perhaps. And so this is how I'm creating the different visualizations that I'll give to participants. We can think about this temperature forecast as sort of a fine-grained state, because I care as a participant about the temperature as well. And this fine-grained state of temperature can map to this, higher level state that I care about of freezing or not freezing in a predictable way. Basically, is the temperature less than or equal to 0? So in any decision problem, we have to have an action space, which describes the actions that a participant can choose between. And so here the actions are to salt or to not salt the road. And then we're going to take the data that we've generated through this data generating model and visualize it. And the intuition here is that, the visualization conveys something about the distribution over the payoff relevant state. And so I'm going to walk you through now sort of what it means to be a rational agent. So a rational agent is an agent who knows something about the data generating model. For instance, they know perhaps the prior probability that it's going to freeze or not. And they're going to then use the visualizations to infer information that they can use to update their beliefs about the payoff relevant state. So imagine I show a rational agent a visualization of the mean temperature with a 95% confidence interval. So the rational agent is going to know how to interpret a confidence interval. So unlike perhaps our behavioral participants, they actually will understand how to do that. And so then they know that we're talking about a normal distribution that looks something like this. And they know that what they care about is whether it's going to freeze or not. And so they can use the visualization basically to infer the probability that it's going to freeze. And so this defines sort of the best possible use of this visualization. And in a case where the visualization does not show directly the posterior beliefs, the rational agent, we imagine, updates their beliefs. In many uncertainty visualization studies, we're actually giving people the posterior probability they need directly in the stimuli. So here, the rational agent doesn't even necessarily need to know the prior. They're just going to read this information from the visualization. And of course, the rational agent is going to come to different estimates as we give them different stimuli. So as we increase the standard deviation, we can figure out exactly what we think the rational agent's going to infer about that probability. Finally, this rational agent knows that we're scoring their decisions using some payoff function. And so they are going to select the utility maximizing decision under their posterior beliefs. So they form these beliefs about the probability of the uncertain state, and then they choose the optimal action. So this is sort of a standard decision theoretic setup where we're defining the normative decision. All right, so as I said, what we want to do here, or the reason we're doing this, is to get these bounds. And so we want to define, this value of information, which will help us understand the value of visualization. And one way we can use this kind of framework is before we've even run an experiment. So imagine I'm trying to design an experiment. One thing that I want to know is that there's ample room between the rational agent with the prior, this baseline, which is sort of the dumb strategy. What does the rational agent do when they don't have access to the visualization? Versus the rational agent benchmark, which is, how well they can do if they have access to the visualization. If these two are very similar relative to, the lower bound on the scoring rule, which here might be 0, then I don't have a lot of room in my study to see anything really interesting in terms of real differences based on sort of a better visualization. So I wouldn't want to run that study. It's sort of dead in the water. What I want to see, ideally, is that the dumb strategy that doesn't even involve the visualizations is fairly far apart from the best possible performance, which is going to be with the visualization. I can also then begin to ask questions, even before I've run the experiment, about what is the difference or the expected loss of performance relative to the best attainable, because I'm giving people visualizations that offer different amounts of payoff relevant information. So, in a case where, I'm running a study, perhaps where I'm giving some, one condition is just the mean temperature and other conditions give variance information, well, then I'm going to expect that there's some loss in performance simply because I gave people a visualization that does not contain as much information. So I can actually quantify that loss of information by calculating different benchmarks for different conditions in my study. So I've sort of separated out that loss. And now I might run my experiment, and post-experimentally, we can use the same approach within this rational agent sort of analysis to now disambiguate other sources of loss in performance. So we can ask, for instance, what's the loss in people's performance relative to the best attainable performance because they didn't seem to get all the relevant information from the visualization? Or what's the loss from people not necessarily having trouble getting the information, but having trouble responding and choosing the right action conditional on the beliefs they had? So let me give you a sense by walking through an example of how we can begin to sort of decompose these losses as well. So here I'm just going to imagine I'm looking at a single visualization, these means with confidence intervals in my fake study. I have this benchmark I've calculated, I have the baseline I've calculated, and now I'm going to run my study and gather empirical data from humans. And I see that their score distribution, the expected score distribution is a little bit above the baseline. So what I now want to do, is understand, for instance, how much were they struggling with the intervals because they couldn't get the information, the relevant information that this interval presentation provided. And so the way that I can think about this is, well, there's two types of errors. Once I give these agents the visualization, there's two types of errors they can make. They can either not get the information that's in the visualization, or they can get the information and they can fail to choose the right answer conditional on that. What I'm going to do is use the notion of a rational agent to fix one of these types of errors, this second type of error, which I'll call optimization loss, which is not choosing the optimal action given their beliefs. So I can take a rational agent and I can use the rational agent to calibrate the human participants' decisions. And the way I'm doing that is basically I'm simulating the rational agent doing the same experiment, but now instead of giving the rational agent the visualizations, I'm only going to give them information about the human decision. And so the rational agent has to learn from this joint distribution over the human decisions and the state. And they're going to basically fix the behavioral agent's errors when it comes to choosing the right action conditional on beliefs. And so now I've basically captured this optimization loss in this difference between the behavioral agent's expected score and the calibrated behavioral agent's expected score. I can now look at the difference between the maximal attainable performance, this rational benchmark, and the calibrated behavioral agent score. And this tells me sort of how much performance was lost because people could not extract the relevant information from the visualization. And so this, in a way, sort of helps guide me towards understanding what's going wrong with different types of visualizations, in addition to knowing, of course, what's the loss of, decision relevant information simply because the visualization format doesn't give me as much information. And there's other types of losses we can begin to conceive of as well. So if we didn't give people the prior, and we had a visualization task where you sort of needed to know the prior to do the optimal thing, or to optimally try to respond to the question, then we can also characterize and think about things like prior loss and try to distinguish that. So we get a framework that allows us to sort of separate things out. So, this is not something that only works on sort of contrived example experiments like I used in this talk. We've actually applied it to various visualization papers, including some award-winning papers. So these were both papers I was an author on, because I think it's easier to critique your own work, or more acceptable. And so, in both of these cases, we spent a lot of time designing these studies. I think, like many people, we're trying to design these decision tasks, and we're sort of relying on intuition and sort of experimentation to try to figure out, like, how do we make this task hard enough? How do we make it so that the visualization matters enough, et cetera? But even despite all the work we put into these papers, this framework, this rational agent analysis, still allowed us to, discover new insights that we had totally missed the first time around. So, for example, in one of these papers, we found that there was this difference in how well different visualizations did in terms of people's ability to make good probability estimates versus good decisions. And we had, come up with sort of some complicated speculative conclusion about why we saw this difference. And using the rational agent framework, what we found was actually there's a much simpler explanation, which is based simply in the difference in incentives to do well on these two tasks. So it gives us sort of an alternative way to understand our results. And another study that we looked at, we found that there was actually little incentive to consult the visualization. So this rational agent baseline, where we're assuming the rational agent just knows the prior, got you more than 90% of the way to the best attainable performance. And so this means that a participant in the study who made a good guess about the prior could do pretty well, and they wouldn't even necessarily have to look at the individual visualization. So that's kind of not what we want. So, in terms of, how I've kind of changed my thinking on experimental research and evaluations of visualizations, one of the things that's become clearer and clearer to me as I've sort of, applied this kind of statistical decision theoretic lens to uncertainty visualization is that we really need to be careful about what we're communicating to our participants if we want to be able to interpret our results as sort of evidence that people are doing poorly with visualizations. So, anytime I do an experiment, I design some task, I have induced some decision problem. Even if I don't think about it that way, there is some scoring rule I'm using, there's some data generating model, there's some uncertain state. And so the problem is that often we do not communicate that fully to our human participants. So we give them some information, but we don't tell them everything that they would need in order to optimize their behavior. The problem with this is that then different participants in our study are going to make different guesses about sort of, well, actually, what is this prior? Actually, how am I being scored? And we don't really want that, because when they're making different guesses about what the decision problem even is, then we certainly are going to have a hard time understanding sort of who did badly and who did, well. We're not going to be able to separate sort of the errors or the loss simply because they were trying to guess our decision problem. And so what this gets at, I think, is that we really need to analyze behavior in the decision problem that we are inducing when we do a study, if we ever want to have the hope of, moving from our experimental results to the world, which is going to be even more complicated. So, one takeaway in designing studies from all of this work I've just shown is that if we want to have an interpretable visualization experiment, or evaluation, we have to communicate all of the necessary information that an ideal agent would need to optimize. So we're not saying that people necessarily will do the optimal thing, but we at least have to give them a chance to do well along the scoring or the performance scale that we are evaluating them on. And so, I think when it comes to the title of my talk, the meaning of quantified uncertainty is its use. One way you might have initially interpreted this is that we have to do empirical studies. And I believe we do have to do empirical studies to understand the value of uncertainty visualization fully. But, the reason I chose this title is actually this different interpretation, which is that we can't really understand the value of uncertainty viz without also considering the theoretic usefulness of the information to the decision problem. So there's two ways to sort of think about this statement that the meaning of quantified uncertainty is its use. So what I've shown today is this widely applicable decision theoretic framework that allows us to bound performance and define the value of information. And this is useful for interpreting results. And I think it's easy to think that this kind of framework that's based in statistical decision theory is going to require you to design your studies completely differently, or, it can only be applied if I've already, designed my study using decision theory. And that's not true. So the only sort of reasons why you couldn't apply this kind of approach is if you don't think that it's possible to define ground truth for your task. So something where you're studying, say, emotional responses, you could not apply this approach. And the only other reason is if you...
Jessica, sorry to interrupt. Thanks for the great talk, but the stream might cut at 11:30. That's what they just notified. So,
yeah, I'm almost done.
I'm so sorry. I mean, if there are any questions, please take them offline. But I just wanted to let you know. I hope
Sure,
they cut it at 1:35, but let's see. Yeah.
Okay, yeah. Yeah, this is like my second to last slide. So yeah, so just summarizing, we can apply this kind of approach pre-evaluation, post-evaluation. It's also possible to relax the assumptions that we're making on what the rational agent knows if we want a tighter benchmark, because we're not giving, or we didn't give participants everything they needed to optimize. And so just to conclude, I think there's lots of important questions for future work and uncertainty visualization that lie on this sort of intersection between empirical and theoretical justifications. We can think of, what are other loss sources we can conceive of? How can these tools help us understand different types of uncertainty, like predictive uncertainty? And, a particularly interesting question, I think, is, when can we actually not apply theory easily? Like, when is the notion of a rational agent not going to help us understand some uncertainty visualization because it's not going to be well defined, how a rational agent would use this information. And so this is something I'm thinking about currently that comes up when you have a distribution-free uncertainty quantification approach. It then becomes hard sometimes to figure out how the rational agent would even interpret that. So anyway, thank you. If there's any time for a question or two, I'm happy to take one.
Thank you so much, Jessica. That was really interesting. I also really appreciate that by the time I had my question, you then had a slide that actually totally answered it, because I was thinking about evaluation stuff and some of your previous work. So I think we should probably just take questions onto the Discord just in case the Zoom goes down. I don't want to interfere with any of that, but I also want to just quickly wrap up and thank everyone for helping us have what I think is one of the best uncertainty viz workshops that we've had so far. I just want to quickly mention
Yeah, I think something went wrong on Christie's end, but in the meantime, Jessica, I had one quick question. Like, have you tried all this stuff that you have been doing on like some scientific visualization data sets? Like I saw like everything
is becoming.
Oh, she's back.
So,
okay. Yeah.
Yeah,
Sorry.
so this work is becoming so really important. So I'm really excited to see so many people involved with it. So thanks again.
All right.
See you so much. We'll talk later. Bye-bye.
See you. Bye.
Thanks, everyone.
Thank you.
Thanks. Did you want to ask your question now, Tushar? Or?
Yeah. I mean, if you have time, you can just
Sure.
say it.
Yeah, I do.
I didn't know. Yeah.
Yeah, sorry. It went so long. But yeah, so your question is if I've applied this to any scientific visualizations?
Right. Like we have these all 2D, 3D data sets and all these kind of decision-making frameworks. Have you ever thought of doing such experiments on scientific data?
Well, we can do it. I mean, yeah, I think it certainly would still apply as long as you are studying something that can be construed as a decision problem. So as long as there is some payoff relevant state and there is some variation in that state over like the set of decisions you want to evaluate on, then yes, because what we're really doing, I mean, there's when you set up any sort of evaluation study, you're choosing, your stimuli, your data, and, how you're going to visualize that. And that induces basically this joint distribution over the uncertain state and these signals. And so it doesn't matter how complicated your joint distribution is, we can still analyze it this way and analyze sort of, the expected performance. Where it gets interesting, is that there are going to be differences in how, a rational agent uses information. So like a rational agent, if there's a rich sort of joint distribution, like high dimensional data, if there is some signal there, the rational agent will still pick that up. Whereas, a human has cognitive limits and might miss things. And so so there's interesting work, I think, to do to sort of figure out like what are sort of slightly tighter upper bounds in these cases where we want to, like, we can model, the cognitive constraints or something, or make different guesses about how humans might be limited, and then try to calculate performance under that. So we've been using it in like AI and, like things like model explanations, which become sometimes kind of complicated. And it can be used in that context as well to figure out like what is the actual decision relevant information that I get in this model explanation, for instance.
Right. Yeah. That's nice. Yeah. I think we should definitely investigate the same ideas in SciVis area, and that will be really exciting. So yeah, thank you all for attending the this great workshop. I think it was really wonderful. So let's be in touch. Thank you. See you.
Thanks.
Thank you, everyone. Take care. Bye.